special announcement. So today we'll break it into two. One session is on cloud resource provisioning, and the other session will be in the next hour will be on genetic algorithm. So if you have any questions, prepare that, and the guest presenter will be the coordinator. Okay. Now, today we will be talking about economic-based. What I mean by economic-based is not spatial algorithm or spatial resource provisioning, but it is the models that take into account the economic aspect of resource provisioning within distributed systems. Now, if you look at any distributed systems, in particular these very large systems, the performance of the overall system depends on the load on the system. And this affects basically the aim of both the user aspect as well as the service provider's aspect. So if the system is loaded, then if you look at from one point of view, the service provider is making money because there are a lot of jobs. But in another aspect, if you look at it, some of the jobs may not actually doing what they, progressing toward their aimed quality of service. And that causes violation of service level agreement, which I'll talk about both of these concepts. So it does not actually matter which way you look at it. It does actually cause serious problems both to the profitability of the cloud service provider as well as to the experiences that the cloud users receive from the cloud data center. Now, to actually address a lot of these problems that occur due to this loading issue, data centers, in particular cloud-based data centers, use what is called server virtualization and consolidation. So we did talk about server virtualization before, but we did not actually talk about consolidation. And today we will actually look at how they use the concept of consolidation to handle the issues that arise from the maximum load issue. Now, the reason that maximum load happens, it does not actually happen all the time, but it is really timely. Sometimes it is underloaded, sometimes it's overloaded, and sometimes it's a normal state. But most of the time, it's actually underloaded in many data centers, unless this may be different in public cloud, because public cloud can be used 24 hours around the world, and that actually increases maybe by a bit the resource utilization within data centers, but not actually really much. Research shows that it is fairly common to see a lot of underutilized resources in cloud data centers. So today we will discuss two possible ways to address this situation, the loading situation. We will look at the reassignment approach, because the higher the maximum load on the system, the longer that each application takes to finish, which means there is an impact on the revenue received by the service provider as well as on the quality of service achieved by the user. So we need somehow to balance this load to ensure that the load is in a good situation. Now, the other approach that I will be discussing today is to see if we can actually, if cloud providers can actually lease resources at the time of experiencing load overload, work overload, to actually minimize some of important jobs quality of service violation. So these are two possible ways that you can actually manage the maximum workload. Actually, there is a third one that I didn't put in. This basically assumes that we already have overloaded situation. So this is what we call detection and resolution. So you detect that there is overload, and then you come up with a solution to address the overload. Now, there is another approach called prevention from this occurring. So this prevention is what's called admission control. So we can have here, if you want to classify this into two, detection and prevention, or resolution, and prevention. So prevention will allow you from occurring. So you only admit workloads provided that your system is stable and at certain utilization level. Anything above that, then you can actually say, I can't actually handle this unless you are happy to wait for such a time or you don't demand quality of service. So in that case, if the user agrees, you can take in the job. Now, the problem in here that many people work on is when there is already, you see, remember we talked about three different fee structure for public cloud. So the one is the on-demand, reserved, and instant, right? So spot instant. Now, a lot of people, including us, we actually work only on demand-based. Now, the reservation, actually nobody looked at it. So in that case, there is actually a lot of things to do here, because we only look at the load when there is, all the jobs are on demand. But if you already reserve some resources, you paid for it already, right? And the service provider did not actually anticipate that they will get into this overload situation. So you come in and want to use your reserved resources, but it's being overloaded. What will you do? How would you solve this problem? Would you actually evict some of the jobs running or some of the jobs queued? So which one of these jobs if you do? So there is issues that I have not actually included here, but you can see that the complexities and the challenges of the problem depends on the fee structure as well. Okay, so from cloud service perspective, as usual, we have users, a set of users who actually send requests to the cloud service provider, which owns the resources, and this could be storing data or running some applications on these resources. And so this cloud service provider provides these resources on pay-as-you-go basis or on reserve basis, sometimes even on availability of or underutilized resources and using spot instance situations. So these consumers will make use of all those three fee structuring to use these virtualized resources and pay for it for the time they used. Now, this basically says duration assuming that it is either spot instance or on-demand provision of these resources. Now, if it is reserved or on demand, it is always the charge is fixed. If it is a spot instance, the charge can change. So that dynamic change also brings an additional challenge to ensure that these users are happy with the service they received from this service provider. Now, so what are the cloud service users are interested in? Because they pay for the resources they used, they actually interested most of the time to minimize their cost. So if you look at this, a given cloud service user used n resources. These could be storage, disk, and CPU, memory, CPU, and disk. And they actually pay for each resources that used. This is the amount that they pay for each resource, and the duration is time. So if you multiply these two, you get, and sum it up all together, you get the overall cost to the user for using these resources. Now, in here, CI denotes the cost of resources, resource RI, which is a disk or CPU, per unit time, which is this one, and D denotes that the time, the overall time for which resources are used. So this gives you the overall cost of these resources. Now, we could actually add in there network as well, right? So sometimes the service providers don't charge you if it is the communication is within the data center, but they will charge you if it is outside the data center. So in that case, you can also add some cost aspect of network. So if we actually look at, as an example, we have resource 1 costing 2,000 rupees per time unit, and R2 is 3,000 rupees per time unit, and we used 20 time unit R1 and 19 unit R2. So our overall cost is 101. Is that correct? 2,244. Yes, it is correct. So it is this money rupees that you pay. Of course, if you pay this amount of rupees for just running something less than an hour, you demand for some sort of guarantees. That is where the issue comes in. Okay? So cloud service users, because they pay a lot of money for using the services, they request guarantees for quality of service. Now, this quality of service is basically one word or one concept, but in resource provisioning, it actually contains many different metrics. Some of these metrics are deadline, some of them are reliability. So when we say deadline, I have an application that this application has to be finished within this deadline, with this time frame. And that is one part of quality of service. Another is budget. So you can say, I only have 100,000 rupees, and this job can only, I can only send it to you if you can actually finish this job within this budget constraint. So these are just examples, but there are also costs, as you saw there. There is resources are provisioned in a cost-effective way to actually minimize the cost. So these are some of the components of quality of service. When we talk about quality of service, sometimes we only talk about deadline, particularly if you're looking at real-time jobs, which are really demanding to be finished within deadline. Some applications, such as workflows, depend on the output of their parents for the data. So there is also deadline for that kind of applications. Budget, as I said, is again based on really cost. Now, if you look at actually these three constraints, these three metrics, they are really interrelated, very much interrelated. So budget and cost are related. So you want to minimize cost, which means you actually wanted to stay within your budget. You don't want to pass that budget. And if you have deadline, deadline is T in here. If you look at this formula, that is T, right? Basically, the amount of time you spend, the more you spend, the more you pay. So deadline, if you reduce that T, you can achieve basically this one. So these formulas, these metrics are interrelated. And we really need to be very careful when we work around these different metrics or constraints. Okay, so one of the objectives of the cloud service users is to minimize their overall cost. Okay, so by minimizing their overall cost, they actually minimize, as I said, all this. By minimizing this, you actually minimize the time it takes, right? And by minimizing that, you also minimizing the budget. You can actually basically remain within the budget or a little bit above or a little bit below. So the cost, the overall cost is one of the main quality of services that basically captures some of these metrics like budget and deadline and so forth. Any question if you have, please don't afraid, you can stop me. So now we actually, as a user of cloud service, we actually encapsulate deadline, budget, cost, whichever metrics or into quality of service. We encapsulate it, we wrap it into quality of service, which becomes just one metric. So, and in this case, our quality of service is just to minimize the cost of using the service. Now, this quality of service is actually presented in what is called service level agreement. So basically, service level agreement is something that you negotiate. This is the service that I am buying from you for this amount of money, but if you agree to it, this is how much, this is the level, the quality level that I'm expecting. If you agree with it, then I can go ahead to work with you. If you don't agree with it, then let us negotiate appropriate terms.
Sir, when we're talking about this service level agreement, so there may be the three types of the agreement, like the technical agreement, functional agreement, and non-functional agreement.
Technical?
Functional and non-functional.
Okay.
We should include all the three, or we should only concentrate on this technical agreement?
To tell you at this level, at where we are in cloud computing, we actually basically don't talk about functional and non-functional. We really say most of the time, if you we look at the cost. We just wanted to minimize cost to ensure, to guarantee that this service level agreement.
There is a one service which minimum reliability and the maximum reliability.
Mm.
So this is possible with the same service.
Reliability is, yeah, one of the quality of
Like
service.
say, suppose that there is any service so that has the two versions, one is the less quality, another is high quality.
Less soft and hard quality, is that what you mean?
Whatever the quality we say, this
Okay.
quality or security, one service is the less secure, another is the higher secure.
Yeah. Yeah, okay, so
we have to consider both.
so one service is less secure, but why do you go with the less secure one?
So that is the cost function. Suppose that my budget is limited.
That's good question. So basically, he wanted to achieve, because his budget is limited, he wants to achieve the result, the application that he wants to execute in the cheapest possible way. Now, that actually affects the reliability of the service providers, right? Some may be very, very weak, very insecure. Some are secure, or some are reliable. Some of the service providers are not reliable. Now, there is a connection between them, right? So if you have very limited budget and you don't care about the security of your jobs, it's okay to go with the cheapest one. But if you can, so it is, in another way, you also buying the service itself, right? The quality itself, in this instance. So the lower quality, the cheaper, and the higher the quality is, the more costly. But in real life, this may be true and this may not be true also, right? Some people, the perception is very important in here. Some cloud service providers may be weak in security, but the amount of the money they pay in advertisement, in recruitment, in some things like this, users can perceive it is more secure than the other one. So this issue is very, very important. Nobody actually looked at, but we already know there is association between the quality of service and your budget. If you have low budget, you go to bazaar to buy clothes. If you have high budget, you go to the mall to buy some clothes. Mind you, sometimes the quality is the same, but it is where it's sold and how it is actually presented. So it is a very good question. I don't know how to really give you a correct answer here, because in main cloud service providers, so if you look at Microsoft, they have built many years of reputation. If you look at Amazon, they have built many years of reputation. But we know that Google is the same. We know that they have failed many times. Reliability has been shown that when they fail miserably. Many areas actually could not get access, many organizations. Now, sometimes you have no alternative. Sometimes you do, right? So far I have not seen an organization that provides cloud services which says we can provide you very cheap but our security is weak or our reliability is weak. So it is very difficult unless we can simulate this and talk about it. Yes?
Can be taken up as a multi-objective environment itself in this case?
Multi-objectives?
Yeah.
In this particular case?
Yeah.
You mean if it is low quality, we will use this. If it is high quality, if it is low budget, we will use high quality. If it is high budget, we will go for high quality.
You can solve a particular problem in terms of identifying all those cases where we have the reliability and cost.
But the problem is, where do you get the information?
That could be, even in this case, we have to calculate somehow. Maybe on the historical basis or maybe some other.
Where do you get the historical data? That's why I say we need to simulate it, because Google will not give you when they failed or when they how their secure is, how many times their system is weak. So we can simulate. But when we do this, we make sure that we try to emulate the real system, because nobody will believe you if you actually simply model a system that fits just your ideas, your solutions. What we can try is, when we simulate, we make sure that we simulate something reasonable, very real. We can say maybe the system fails 0.1% of the time, or 1% of the time, instead of saying 50%. Now, if you say Amazon fails 50% of the time, nobody will believe you. So you can get data, but you can actually make sure that this data has to be very realistic when you create your own data. So now, service providers are interested in increasing the performance of all the applications, as well as improving utilization and thereby minimizing the usage cost. So these are some of the objectives of the cloud service providers. The first one, and the most important one for them, is to increase their revenue. This is very, very important for them. If they are in cloud service provision or in business to make money, so this is obvious. So they need to actually increase revenue, particularly because they are also people who bought the stock in this company. And you have to make money, at least some billions of dollars per year. This is the most important criteria or metrics for cloud service providers. Maximization of utilization, resource utilization is another one. Again, this has to be done in a very controlled manner. If it's not controlled, you will get into a situation where you can violate a lot of service level agreements. So here is a research question related to cloud service providers. Now, because requests from the users come in unpredictable manner, and we want to develop an approach that predicts future resource requirements for workload. This predictive approach can lead to better resource efficiency. We have to show that, if we look at the arrival of the jobs from traces, can we come up with a predictive algorithm that help cloud service providers to ensure that they can provision resources or plan ahead to minimize the resource utilization issue. Now, what this will help is, if you can develop this, not only minimize the overutilization of resources, but it will improve resource utilization in many different ways. One is by basically telling the cloud service providers, you will have 80% of resources underutilized. Why don't you actually now sell it as spot instances, at least 50% of it, and keep the 30% of predicted underused as a contingency. So if something happens, you can still have this 30%, but 50% instead of sitting, you make money. So you can use this in many different ways. You can avoid overloading, you can also bring in some more money and so forth. So can we do it? I believe you can. It's in fact not a hard problem to develop. Okay. Cloud providers must achieve also, because of that certain level of quality of service, required, for instance, for budget constrained jobs, the cost of performing these jobs can't exceed the budget constraint. Therefore, one of the challenges facing this service provider is how to complete jobs with unpredictable submission time. So this is another one. Jobs come in, okay, in unpredictable manner. How to actually complete these jobs, which leads us to this second problem. Now, most of the existing works don't consider unpredictable submission. They all consider predictable. So, there are some which considers unpredictable, but I said most of it, not all. As well as budget and deadline constraints simultaneously. So, because quality of service with jobs and budgets comes in, can we actually do this? Can we develop a system that mainly looks at unpredictable submission of jobs with budget and deadline constraints? So you can actually combine these into cost if you want to. So can we do it? Because this will add some knowledge to existing research. Okay? Questions?
Sir, what may be the aspect of this unpredictable submission?
What is?
The aspects of the unpredictable submission.
Aspects of unpredictable submission?
In some cases, why it is unpredictable?
Is it 2 days ago or on Friday I showed you some jobs? Sometimes we have really very regular job submission, and then all of a sudden the jobs go up and then spikes up, goes down, spikes up. So you can't actually predict when these jobs are coming. So for example, if you use reserved resources, now most of the time these people actually reserve resources, the cloud users, but they only use it when they are pressed for using these systems, right? Otherwise this will stay idle. What the cloud service providers will do is they will use this until you need it. When you need it, they will migrate the jobs from it. But how can this is unpredictable when they come in because there's resources.
Sir, it might be a case that a service demand at a one particular case. Let's suppose that at any particular time or any particular day the service demand is going to be increased. So we can predict that particular situation.
Yes, you can actually predict. But what I'm interested in here is that to couple it, to make it multi-objective. Okay, use the prediction that the problem statement we stated earlier, but now I'm interested in coupling with some metrics. So can you actually minimize? See, what we're minimizing is that we know these jobs are coming, so we can minimize for these jobs. That's how we formulate. So n jobs are coming, but if we don't know that these n jobs are coming, your problem formulation becomes a little bit out of sync. So if you're expecting 20, your n is 20, but you received 40, and you said we're doing it for n is 20, but you got only 1. So how do you actually deal with this? This is uncertainties. So some people actually also deal with uncertainties of dynamism of the job arrival and the cloud resources itself, which is actually another version of this, how to deal with uncertainties of the environment. So here is the service level agreement. Service level agreement, SLA forms an important component of the contractual relationship between a cloud customer and a cloud service provider. So it is basically a binding document or a binding agreement between these two. So this actually said, I will give you some service of this level of quality, and the cloud consumer agreed with that level of quality of service. Actually, we have written a paper on this service level agreement here, published in the Journal of Supercomputing, and we have also written a paper. I just forgot to put it in there, the negotiation between this and this. It is in IEEE transaction of service computing, so you can actually find that how we negotiate based on utility optimization. You can actually, in game theory, this is where I wanted to bring game theory here, and you can actually do some sort of negotiation here. So here is another research question. Different cloud service and deployment models will require different approaches to SLA. So there are different deployments. For now, we simply talk about SLA in abstract. So we say for everything SLA, but we do know actually these are the issues. How can we encapsulate these different issues into this abstract SLA? This is one of the open problems. Research question 3, the global nature of cloud computing renders SLA to cross several jurisdictions. Frameworks for handling data privacy is an important addition to cloud computing. So this is another one. So if a cloud computing is in India, and now you're purchasing these resources from, say, China, then there is an issue of this service level agreement. So how can we actually come up with a framework that can handle, as an example, this is just as an example, but there are many, many issues that we need to handle in here. So service level agreement is not an abstract entity, really. It involves negotiation, it involves different agreements, sometimes also different jurisdictions. How can we deal with it? Now, another important, these are actually, I'm just picking up from this paper. Another important problem is that we actually, we can create a template, right? The way it is now is there are templates sitting here. And these are the templates you use to negotiate this service level agreement. Okay? So instead of that template, can we come up with a different one for different users, but at the same time to minimize the number of negotiations, the iterations, and the different types of SLA level? We actually develop some sort of a database where users can actually go and see, or at least don't give them, delete the names of the negotiators there, right? But you give them access to see which of these, or at least develop a system that recommends which of these service level agreement that has been used will be usable to them, or will be favorable to them. Instead of writing and doing agreements, these users can actually go in there, find one that's suitable for them. If they want to modify, make little modification, then send it to the cloud service provider, because the cloud service provider already accepted this SLA before. They can now simply stop negotiating because they can do this already. They have seen it. They have done it.
So kind of a recommender system.
Recommender system, that's what I'm saying. Put in recommender system in here so that the user, the time the user and the service provider spend will be reduced. Okay? So these are the kind of things nobody has done. So I'm just giving you to jump on it and do it. So one of the problems with SLA is that the service provider is bound to some penalties. Now, there are many different ways to express the penalties. This is one way, okay, that is expressing the penalties. As I said, there are many different ways. This is just one. So, now economical penalties for service level agreement violation is the sum of the total proportional penalties cost for unmet demands of resources. So we agreed that you will be providing me these resources, but you have not provided me, then this is actually coded in service level agreement. So if you see, the formula is basically saying this penalty at a given time, at given instance occurs. So the R is the number of resources assigned, this one, assigned to the cloud users. So this could be, for example, disk, CPU, RAM, memory, and network capacity has been assigned to you. In this case, R becomes 4. So you used 4 resources. And M is the number of virtual machines that you have used. And RK is basically revenue for if you completed this job based on the quality of service and service level agreement. This is how much the service provider will obtain. And this is basically saying that which of these resources are actually failed. So the service level agreement, maybe 3 of them met the service level agreement, but 1 of them failed the service level agreement provisioning. Now, this is basically the penalty factor for resources, for each resource, and this can be greater than or equal to 1. So basically this formula says this is how much you're supposed to make, but because one of these or all of it did not achieve, this is how much you pay. So this could be negative or something very small or very high. I know that Professor DP and Professor Dyer have worked something in this area. I know also they have different formulation, but as I said, there are completely many ways to present this. Okay, the interest here is many people actually say if service level agreement is violated, we just consider as all violations. What this formula says is that actually some of them met the quality of service. If disk met the quality of service, then this becomes really 0. You don't charge that amount to the particular disk, CPU, or whatever. If the network is the culprit, then we charge actually the amount that the network cost to delay the execution or the completion of the job. This is one way of looking at it. Or another way of looking at it blankly, okay, just saying that violation is violation, whether it is violated by one component or violated by all components. Okay? Any questions?
The degree of violation also may be included in this to provide the penalty. It is not that blankly due to network, if it is failing, so charge a fixed amount. It will vary as per the level of service achieved or the degree of objectivity achieved.
That is correct. But we don't put that in this because when you make the agreement, service level agreement, you agree that plus or minus some level. So they will say we will give you at least the 100% we promised. Sometimes we'll give you even 90%. Sometimes we'll give you 110%. So you agree that leeway is always built in the service level agreement. In particular, if you have unpredictable system that dynamically change, you can't simply come up with service level agreement that says 100% of the time I'll give you this, because you don't know what's going to happen. Any other questions? So, you want to take over or?
You continue, and
Okay.
then I can take second half. No?
Yeah, okay. It's 11:30, that's why I say.
No, it's you can continue because
Okay. Now, cloud resource provisioning algorithms. Now, there is a lot of, remember, I told you a lot of metrics that we use, deadline, budget, and this. So, a lot of resource provisioning that are specific to this particular metrics have been developed. Now, you can see if you actually Google, you will find a lot of algorithms with budget-aware provisioning. So the objective is basically to complete these jobs such that the cost of performing this job can't exceed a certain budget constraint. So these are their objectives. Cost-aware is another algorithm that is common. Again, is to satisfy the service level agreements of the user while minimizing the total cost. These are common market-based scheduling policies. Another set of scheduling algorithms or resource provisioning is SLA-aware provisioning. Again, if you look at this, the objective is to satisfy the service level requirements of the user while minimizing the total cost. However, in my view, the SLA requirements consists of budget and deadline. To prove this, let us look SLA aware algorithm. The objective is to minimize total cost. Okay, so this is the cost of resource I and how much time you use. And this is called total cost, and subject to the total cost must be less than or equal to the budget, and the execution time should be less than or equal deadline. So by having SLA aware provisioning algorithm, we can actually have the both deadline and budget aware algorithms. So the question is, then why do we keep developing and talking about simply budget, which includes SLA, which includes quality of service discussions in there, when we can actually just develop SLA aware algorithm that actually simply captures all of these criteria or constraints that we need to deal with. So when you read papers, basically watch out and see if you can actually make sense of exactly what they're doing. Sometimes it is confusing. In the document, they talk about service level agreement, and the title says cost aware, and so forth and so forth. So I just wanted to give you this idea because most of you will spend reading a lot of papers to see, to find some open problems. So we know that they receive a lot of requests in a dynamic manner. They need to place these requests also dynamically. Now the requests have also different characteristics and also different dynamic parameters. All of these jobs have this. And we know that it is actually very well known that any online algorithm for provisioning resources have some problems when you apply it, because offline algorithm always performs much better than online algorithm, but offline algorithm is not usable in a dynamic environment. When we use online algorithms to make decision, we can actually make a good decision. But as the system runs, because the system is dynamically changing, then the decision, the original decision that we made, may actually require some modifications, some revisiting. This is not actually happen in many scheduling algorithms. So it is both, what I'm saying is we need a resource provisioning algorithm that is reactive and proactive at the same time. So this is what basically we are talking about today, about proactive and reactive resource provisioning. A common approach for optimization, which is reactive after the placement of the initial online decisioning making. Then a common approach for optimization of the VM allocation after the initial allocation is through adjusting resource allocation according to the demands in order to satisfy the service level agreement. So what I'm saying basically is that you made a decision online, and now you need to monitor how much the SLA that you agreed with is holding. So if there is some changes to the environment of the system, then you need also to change the system quickly, or the initial assignment quickly, by adjusting the resource allocation or reallocation of the resources to the virtual machines, so that you can achieve the stated or agreed service level agreement. Okay? So this is basically achieved by rebalancing of initial placement, and rebalancing basically means to proactively monitor the load of the physical machines and dynamically rebalance the load, so that some virtual machines will be moving from some overloaded machines, so to achieve the goal of the performing load balancing, meeting the quality of service, and avoiding also overloading of the CPU resources. So the migrated virtual machines will be redeployed in a normal physical machine, which is different than the original one, but achieving these stated objectives requires a number of algorithms, even though rebalancing looks like a very simple act of approach or act of service, but it is actually very complicated. Now here is the complication. One of the complications arises from the fact that when a host is supposed to be heavily loaded, where some virtual machines from the host should be migrated to another host. So which host will be the receiver? And when a host is believed to be moderately loaded or lightly loaded, resulting in a decision to keep all virtual machines on this host. Oh, okay. All right. Thank you.
Too fast, otherwise there is a...
Yes, I will stay this way. So basically what we're saying is that you have some situations, 4, 5, 6 situations that complicates rebalancing. You have on one machine, you have 4 virtual machines running. Which of these virtual machines will you be moving? And how many of them will you be moving? So this is one issue that you need to deal. How many, which one? And if you have multiple hosts to receive these particular virtual machines that you're moving, which of these hosts will you choose from? On what criteria? Okay? And also, what are the costs of moving these? How much quality of service they will improve? So I can go on telling you really the complexities of this load rebalancing. In standard distributed systems, it was actually much simpler. But when you include this cost, service level agreement, dynamism together, a concussion of complexities will arise, and we need to deal with each one of these. So if your guide sometimes tells you, why you simplify things? Because this is what you need to consider, and always bring this out easily so that you can see the complexities of the problem. If you come to me and you say, I want to develop a load rebalancing algorithm, why will you do this? It will just move virtual machine from overloaded to underloaded. But this is a simple presentation. But I want to see the reason, the causes, the expectations, and the complexities that are involved in this process. Okay? Okay, so one of the problems that we need to look at is the overloaded cost. So this is one of the major problems. Okay, this actually happened. This happened. I am not quite sure either in India or in Pakistan. So it did happen. I don't know. I forgot where it is.
These are common phenomena here.
It's okay.
You can take the example of India also, doesn't it?
No, it could be Afghanistan also. So, so
They are telling this is usually happening in Syria nowadays.
okay, so it could also, it does.
Yeah?
No. We don't use this.
They don't use this bullet. Yeah, the horse.
But look, I have seen this in my eyes in China on a bike carrying 10, 15, 20 kilos on a bike, and the bike and the person is going actually failing. I seen a lot these things happening. Lorry, small lorry carrying 3-4 times of its weight, and just trying to turn a curve and going really fast. But it happened. That's why I'm just emphasizing the overloaded host. I don't mean anything here, so ignore that part of the discussion. So now overloaded can occur only when you overbook a particular host or network, right? Even this, it doesn't matter which resources, you can overload the resource. This could happen in many different areas. Now, the consequence of overloading is the possibility of violating service level agreement. So one of the problem is how to find an overloaded host. Remember, you online scheduling or resource provisioning algorithm, what does it do? It simply assigns virtual machines to hosts, and it never come back again. But now you're actually trying to rebalance this assignment, so you need to find out which of these nodes are actually running virtual machines, which of them are considered as overloaded, underloaded, or normal. Okay, so this is a very important question, in particular if we want to achieve the revenue maximization objectives of the service provider. Overloading can lead to service level agreement violation, which will lead to the decrease in the revenue of the service providers. Now, there are many different ways that are proposed. I will tell you 3 or 4 ways. Okay, this is what we have done recently and just published in Future Generations. She has the paper. And the other day she was asking me this question. I forgot about the paper. I was trying to explain it to her. I think we have done this work. Then I gave her the example. She never said, "This is your paper, sir." She just sat there, and I spent an hour, and then finally I said, "Okay, you can read my paper." And when I scroll down her screen, that is my name is there. I said to her, "You should have told me this before. I would have saved all this time." So this one is recent one. And she reminded me, actually, I forgot about this paper also myself. This one, I am also the second co-author here. Anton was a PhD student, so this is actually improvement over this. And this one, I wasn't there. I don't know if I'm there, I can't remember. But basically, these are three different ways we wanted to partition the physical machines into different classes. So what this actually says is the single threshold says, here are, this is a machine, this is time. So basically put one threshold. Okay, this threshold says this is maximum number of virtual machines that can be assigned to any node. So anything beyond this is the machine is overloaded. Anything beyond this, the machine is okay. So this is how they actually can decide if a machine is overloaded or underloaded. Now, one question is, how did they actually determine this? How do you determine a threshold? So, the aim is to preserve free resources to prevent service level agreement violation due to consolidation in cases when the resources demand by virtual machine increases. They actually, if you read their paper, it is random. Sometimes you can actually look at saying 80% of system utilization, which we know from the traces, most of the workloads hover around between 20 to 60, 70%. So you can say if it is over 80%, that is overloaded. Okay? So that is exactly what happened here. Now, because they basically determine this static threshold method or fixed value of the threshold are not suitable for dynamic workloads as they do not adapt to the changes in workload. So in other words, this is fixed, right? Now, you can actually work on a new problem which we call window sizing or resizing, where you can actually move this along. If you just wanted to use one or two, you can do it actually that. You can actually come up with a host overload detection by using that window resizing. So this is a window based on the different workloads. You can actually move up or down and determine it dynamically instead of as it is now static threshold.
But they already have done also.
Oh.
In 2012, they have done adaptive, and it's there also in Cloud Sense.
No, they didn't do it for one. What they did, I know they used, the one is they used Markov chain. The one they use Markov chain.
No.
Hmm.
I don't about that. I have it.
This is the one you're talking about, double threshold, right?
Adaptive, not static.
No, no, no. I'm talking about this one is static.
Yeah, yeah.
So what I'm saying is use Windows, a different approach to change this and that. So what they used, I can tell you it is Markov chain based approach. Okay?
In some approaches, even they have used the lower half pin and upper half pin, and they have tried to convert this to a solution.
Mm.
So that's also there, depending on the load, because load also continuously changes. The static one applies only when the workload remains the same. But
Yeah.
actually, once the job starts executing, so the workload also comes down.
Yeah.
So it can be adapted. Maybe what is.
Yeah, they have done Markov. I know what they have done. It is called. It uses Markov chain idea to adaptively change it. But what I'm saying to him is that that's very expensive approach. So it takes a long time for the Markov chain or the machine learning approach they used to, you need to first of all, you need to train this approach. They need also to come down to some certain level. Machine learning is very good approach, but if it is online, I don't know how effective it is. I know they did. They call it adaptive, but it uses machine learning. If I correctly recall, somebody can actually check it. It uses Markov chain or some other machine learning. I'm familiar with all their works, but I know that the new one they used they used 3. They came up with 3. Okay, so this is one of them. This is another one. The 2 threshold one is another one. They came up with a third one, which they call it adaptive, because and they use some sort of machine learning in there. Okay, and in fact, one Russian guy has proved mathematically the adaptive approach works, but it takes long time. It has he has recently proved. I reviewed that paper. It works mathematically correct, but it has some time impact. What I am suggesting is a much simpler way. There are approaches we use for many things, sliding window. I believe that you can apply this on this problem by simply adapting the window size up and down, as Professor Zain said. We haven't done that, and I haven't seen anybody applying a sliding window on this problem. Okay?
This interquartile range.
Yeah.
They use interquartile range.
Mm. Yeah, quarter 25,
Yeah,
30,
yeah.
and then if you keep reading, then you will see that this is just one of it. There are 3, 4 of them.
Yeah.
Okay. In the same paper, that interquartile is actually in the same paper where you find this.
Yes. It's 2000.
I am actually the co-author of this. The second author is me. So I'm just I know the third one they did also is without me. Is they use machine learning. That's what I'm trying to tell you. Okay. Now the double. How are we doing?
You continue.
Continue? Okay.
I'll be doing it in the, let's say, after lunch.
After lunch, okay, that's good then. Okay. Now the double threshold, we still try to determine the overloaded host. So the double sets 2 thresholds. One is low utilization threshold, and the other is upper utilization threshold. This is exactly what Professor Diane just said. and to control all host CPU utilization between these two thresholds.
So this is also static.
This is also static, okay? But by changing what we did is actually now a form of sliding window that we wanted to use. That is what they improved on the third one actually. We wanted to put this 1/3 quarter, 25% quarter, 15% quarter, and something like this. But it's not quite the sliding window, the easy, nice one. It's not like that. But it is actually, you can classify this also as static. Okay, because we design with two thresholds.
And you mean to say introducing the working set model?
You introducing the working set model, yes. That's correct. So if you use the sliding window, use the working set model, and then it becomes very good. That's excellent point.
So these all models are for data center load balancing or inside a single data center?
In only one single data center.
So, but as far as the normal distributed systems are concerned, load balancing applies really well because putting the jobs here and there so that we balance everything. But if we talk about cloud in particular, even once the machine is provisioned or a new machine is initiated, energy also becomes an issue.
Yeah.
So that actually becomes very important because if you transfer the jobs between data centers, it works fine because you are overall balancing the loads on the data centers. But inside the cloud, initiating or provisioning more machines creates another problem, which is that of energy. So
yeah, I will address that in one of the.
Maybe the day after tomorrow.
Yeah. So how we actually affects energy, and how we deal with energy management also. Yeah, I will raise that issue there.
These load balancing issues are with respect to VM placement.
VM placement only. So these are only VM placement and replacement. Okay.
This can be done for load balancing and for energy.
Yes.
Or there is upper threshold to migrate from overload to underload for load balancing, and minimum threshold to migrate from underload to another machine and turn it off.
Yeah. So the idea of consolidation is exactly you can use migration. So you can migrate to improve energy, to improve load. So because we are talking about market-oriented scheduling, this is where I'm actually looking at service level provisioning violation in terms of work. But if you look at energy conservation from the point of view that these two questions raised here, is a metric that specifically applies to the owner of the service provider, because the owner of the service provider is interested to improve this revenue. Energy cost reduces that revenue. So I will now focus on this is on both sides, particularly from service level agreement, which holds the service provider not to violate or minimize the number of violation of the service level agreement from business perspective. So today I focus on that only. I didn't mix energy optimization, which is a metrics for service level provider, with the consumer aspect of service level agreement violations. So there is impact actually if you try to move, as Professor Zai said just now, there is impact on service level agreement violation because you try to minimize energy, you are bound to cause also service level agreement. And we will talk about those relationships when we talk about the energy area. Okay?
So at the same time, when we are having this migration cost, which is coming into the picture, being paid off with the overhead cost, I mean, once we are making it 25%, 30%, 50%, something like that, then in that point, when we move from 75% to 100%, maybe that cost may be neutralized in contrast with the migration cost.
that cost will contrast
the migration cost. I mean, it would be an overhead cost because of overloading.
Yeah.
And when we have to migrate it, I mean, there would be another cost which will be added on it.
Yes.
So, will there be anything that we can discuss about the trade-off that would be needed beyond going 100% or before lying in the range of 75% to 100%?
Yeah, so I am actually discussing that. Here, I will be talking about it. So if you can wait a little bit. But it looks like people are very fast. Here is the two basically, if you have two thresholds, then you can actually divide it into three classes. The hosts can be divided into three, right? Because if you put two bars, underloaded, overloaded, normal. So that is what they basically did here. Okay? So I will actually, because it is time, so I need to little bit rush here. This is the new one we did. Instead of actually proposing two, we actually did three thresholds. And then you see we call this T1, TA, TB, TC. These are three thresholds. And then we divided the nodes into four overloaded hosts. And these are normal hosts. And we say this is hosts within this zone are little loaded hosts, and hosts which are here is less loaded hosts. So we actually developed this for the purpose of energy. And we have shown this, if you look at our paper, is much better than what we did with Raj and Anton earlier. Because this gives us easily identifiable sections where to move, which one to turn off easily. So, but I will also explain it to you. This is the paper. See, on this laptop, anytime you press 8, it doesn't press. So this is not 2,201 years, but 2018. Okay. So it's a new paper. And this is basically now the threshold we don't determine statically. What we do is actually it's based on the workload. We use the workload, and then we try to create clusters based on k-means. There is many ways you can do this, and so our threshold actually changes dynamically with the workload. You can read the paper. I don't think I should go through this. It's very easy algorithm. Now here is regarding overloaded host detection, an open research problem. In most of the time, random workload is assumed. This is actually common, okay? And the host overload detection method, which is based on a fixed threshold, is incapable of adjusting the reserved idle resources according to the uncertain workload, which hinders the use of the virtual machine consolidation method to properly allocate resources and causes undesired situations such as poor services, performance, and high energy consumptions. Can we come up with a better solution? Okay? Now, the second problem that we face is selection of host. Load selection. Now, which one of these load or workload virtual machine we can select? So, one way to select this is basically to look at the total remaining amount of computation required for processing virtual machine J on computing node I. Then determine the most remaining load is done by simply evaluating this. So this is what we actually use with Raj Kumar, and if you look at many of their algorithm revolves around this, just tweaking little bit here and there. So what this says is basically look at virtual machine that has received most of the processing time, or you can actually look at a virtual machine that has not received. So there are three different virtual machines. One has received the most, or all of them have received equal, or some actually received some, and some haven't received any. So you face this situation. So how do you select the virtual machines that you are going to move? So this basically says move the one that has received the most service. Okay. So the question is, it is to be noted that since cloud resources configuration is not the same, when moving from one cloud to the other, this is now, we're talking about federated cloud. So if you're moving into federated clouds, the computation requirement of a load is different on different computation nodes, because now you are moving from one cloud on one, maybe two cores of CPU. Now you're moving into one core CPU with different architecture and so forth. The challenge is to develop a prediction algorithm that allows a computation node to estimate the computation requirement of a load on the expected node. So if you move from one cloud to another, can you actually estimate how long it takes? So if my job, the virtual machine's time remain is more than moving there, it is useless to move, right? So you need, if you add the time it takes it there and the time to move it there, it is useless. It is costly. Can we actually predict that?
But difficult to measure RIJ also.
It is very difficult. Yeah, it's very difficult. It's PhD level. It's not master's level. So as I said, these are actually some of the approaches that are used in many papers, selecting a virtual machine that has received the most, selecting the host that has not yet received any service, and so forth. Now, these are some of the policies that we actually developed with Anton. The minimum policy selects the minimum number of virtual machines. So if you have multiple virtual machines in a system, then you need to decide how many to select. And this one says just select minimum until the load actually goes beyond the overload. And the selection is based on the fraction of the CPU utilization allocated to the PVM. So how much execution this particular virtual machine already has. The next policy is basically the lowest usage of the CPU. So the virtual machine requested 10 CPU cycle. So it has only received 1. So it is considered that relative to what is requested, it has received very low. So this has to move to another machine. So this is what the highest potential growth is. This says basically randomly choose any one of them. So these are the 3 policies that they provided. So these are basically selection of which hosts to move to and which virtual machines to move. Now moving incurs migration, right? So now there are a number of techniques of migrating virtual machines, but there is a problem. Some virtual machines are very big. Some virtual machines are very small. Sometimes it's possible to simply move straight from here to there. Okay, I have seen also techniques that actually break the virtual machine into a smaller chunk and then move them straight and then reassemble them there. but reassembling can create problems. The messages can arrive in different order, and then it becomes problem. So the best solution is, what you do is that you actually write the image on a disk, and then the other machine that's supposed to actually receiving the virtual machine will simply read it and execute it from there. It's slower, but it is effective. So this is actually one of the common ways of doing this. Now, you don't have to worry about the size, because it's all stored in a external disk. Okay? Now, one of the problems, actually two problems. One of the problems is thrashing. So what happens is that, particularly if you see the random one, or the three policies that I showed you earlier, if you randomly move a virtual machine, there is probability that a virtual machine will end up moving only. It doesn't actually finish its execution, leading to what's called thrashing, right? It just goes A, B, and move A and then there. So we need to watch out of that problem, because it can violate the service level agreement. One way to address this is that we actually keep with virtual machine the number of times, the maximum number of times that a particular virtual machine can migrate. So the selection policy should take into account how many times this virtual machine has migrated. If it exceeds that maximum threshold, then you say, no, this is not actually a potential virtual machine to migrate. But now, again, that issue of what is that threshold, how many times it should migrate, I haven't actually think about it, but this is just a solution that I think we should implement to avoid this thrashing. Another approach is we simply move now, right? We just look at how much time it has received or not received. What I propose is to actually look at workload-aware virtual machine migration. So when we do relocation, can we actually look at the workload that virtual machine is embedded with? So if, say, for example, if I have workload flow and I'm running a parent application in this node, and instead of moving a node that is very close to this parent node to a very far, which is waiting for data from this parent node to another far location, I can actually say, okay, but the child of this child can move, because I can actually send the data to this one, because this is about to finish, the parent is about to finish, I can pass the data here too. So this is a very simple example I'm giving you. Can we actually look at the workload-oriented migration? Or at least when we design the selection policy, can we include as a factor the workload information with the virtual machine? So this has not been done yet. Okay, so this is actually what this research problem statement basically says. Existing approaches tend to be workload agnostic, so they don't look at the workload. They only look how much CPU it has received, or how much resource it has received. In most cases, produce reallocation favorable to the workload. The challenge is to develop workload-aware reallocation approach and compare it with the existing approaches. So here are another research question. The algorithm we developed in PSO, so I'm talking about the 3 threshold algorithm we developed, that's for you actually. If we combine it with the PSO approach, what will be the improvement. Okay? Now, we want to measure that improvement in terms of decreasing the number of virtual migrations, virtual machine migrations, how many virtual migrations migrated, and how many times the violation occurred. We need to develop locality aware. Now, we don't have also locality aware. It's very important that we develop migration, virtual machine migration along this line. We also develop virtual machine that really self-decide. Okay, so what we do now is a policy sitting there and decide for virtual machine which one to move. Is it possible to design an algorithm that actually a virtual machine itself will decide, I want to move because I'm not happy here? Okay, it's just like a wife wanted to be divorced because she's not happy. Something like this. Remember, we used ant colony and all these nature-inspired. Use some things like this. Her wife not happy. She wants to be divorced. The same thing here. So you become very famous because everybody will quote you. Okay? So we want to develop really things like that here also.
What do you mean by the locality? What kind of locality do you mean?
Data locality.
Data locality.
Yeah. So, or application locality. So that's what I mean.
So you mean to say that some machines are having the affinity with some VMs?
Yeah. Yeah. If you look at some applications like IO intensive applications have locality issues. So when you migrate, you could actually look at that data locality issues in there as well. Now, can we come up with a learning automata based load rebalancing mechanism? So it's very interesting issue here. Okay, now I'm coming to your point, cost of migration. How do we compute the cost of migration? So the proper virtual machine migration between servers can reduce a lot of research says service level violation in data centers by actually moving around virtual machines. You can avoid or minimize service level agreement violations. Now, but the excessive virtual machine migration could negatively affect the virtual service level agreement. Now, this is another challenge, but the challenge is basically here to develop a prediction algorithm that allows the computing node to estimate requirement of the load. Here is how we calculate the cost of moving the memory size that the virtual machine needs divided by the bandwidth within the bandwidth, the network bandwidth, and then plus some startup, some if you want to move, you have to do some preparation for the message to be transferred. So this is the time it takes for migration. And every time you migrate a virtual machine, you have to add this TMIC into it is service demand. So because that is what it takes to migrate, and then you have also restarting the whole virtual migrated node that you can add also there. So migration cost is basically, this is the formula that is commonly used to determine the cost. So the other formula I showed you is the time, the remaining time for this virtual machine to finish will increase by that much amount. but this one says this is how much it costs you. So it's basically it's a derivative here, where U2, UG at a specific time is the CPU utilization or by virtual machine, and each virtual machine may cause an SLA violation. Therefore, it's crucial to minimize the number of migration, as I already said, and you basically, I don't know, I can't remember why we multiply by this 0.1 is a constant factor here, and you need to integrate this to get the CPU utilization, and this will give you the cost once you get the value that you multiply it by 0.1. I will, if I remember by this afternoon, I will actually pass on that information to you.
Has it been published somewhere?
Yeah.
Paper might be having.
I will give you the paper. I know it's published there. Actually, if you look it up in that 2012 paper, I think it's there. Okay, this is there. I can't remember why we used 0.1. Okay. Now, research problem, the behavior of application, number of memory pages that the application updates during its execution have direct impact on performance degradation and downtime. Research is needed to quantify this impact. So we need to actually do some implementation or real life situation to see how much this memory pages that application updates affects the impact when you migrate virtual machines. Now this is how we actually calculate violations of virtual machine service level agreement by using two different parameters which are called ATF and PDM. Again, this is in that paper which I just asked him to look into it. I will give you that paper later on. So this is what PDM says basically. The PDM is the overall performance degradation by virtual machines due to migration and performance degradation. So this is the name. Performance degradation migration is equal to 1 over M. M is the number of virtual machines divided by the sum of the estimate of virtual machine performance degradation due to migration. This is due to migration. A divided by the total CPU of virtual machine requested during its lifetime. So usually we keep CDI as 10% of the CPU utilization in all our papers. So I think it's becoming norm because many people start quoting us. Again, the reason we use 10% is explained in the paper. I didn't put it here. The second part, which is OTF, is calculated as 1 divided by N. N is the number of physical machines. And TS is the total time during which the physical machine has experienced 100% utilization, which is causing SLA violation, divided by the total number of the physical machine that is active or serving virtual machines at that particular time. So this will give us the overload time fraction of the virtual machine migration. So these two together will give you, if you multiply them, they will give you service level agreement violation rate. So that is the rate we use to calculate the amount of, in the other formula that I showed you earlier, the amount of compensation that the cloud service provider provides. Now this, so far I basically talked about one solution for load balancing, moving within one cloud, moving virtual machines from one location to another. Now the other option is actually to lease resources. Now this user requests resource from this guy, but this guy is overloaded. So instead of rejecting, particularly if this guy is a good customer or this guy already has reserved some resources, then the other option is to lease resources from a second cloud service provider in federated environment. There is some issues here now, right? Because both of them are in business. So should this cloud service provider sell or lease resources in the same amount as they sell to regular customer, or they charge them 70%, 65%, because this is in business to make profit. And so that fee structure is another issue that nobody actually looking at it, is what is the appropriate. We are just modeling a business model, right? When in supply chain, if you look, the supplier will sell to the another chain, down chain, cheaper, and then that when it goes to customer is more. So is it what if that kind of business model is between them, even the federation then makes sense. Now federation doesn't make sense if actually a cloud service provider will buy or lease resources when it needs it from other resource provider at a full price. Another problem we get into here, what if actually this guy is simply doesn't want to use it, reserving some of its resources for selling it at a premium and then buying it at lower cost from here for all lower quality requests and directing it there. So these guys will lose and this guy will make money. How can we handle that situation? So when we talk about federation of clouds, nobody actually talking about these issues. They only talking about the technical aspect of it. How can we build a gateway to access the resources of the other? But these are in business. These service providers are in business, and we need to also take all these issues into account to make federation real, usable. Here is some formulas for you. The pricing scheme may depend on the price agreement between the two cloud service providers, and this is the cost at each time, instant time t. The leasing cost that a service provider incurs can be represented as resource that is leased from these service providers, and if this particular resource is satisfied within here, or it is actually the xj is basically says the cost is if this resource is provided by this, then it is 0, but if it is provided by there, it is 1, so it is full cost. But that amount of cost we need to take into account when we calculate the revenue that these service providers will get from this client by directing some of the virtual machine requests to the second service provider. One way a cloud service provider may support requested resources that are not able to provide is by leasing resources from another provider. And so an approach that allows a cloud service provider to lease resources from another cloud service provider that fulfills in a transparent manner. Transparently leases low-priced resources from alternative providers. So what basically we need to develop in here is two things: service discovery and recommendation. Now, one, for this already a lot of work, but within federated cloud, we need that. Okay, but that has to be done, which is transparently, and find low resource from alternative providers. Now, the leasing cost should be minimized in order to maximize economical revenue objective function of this particular, of actually both of them, because both of them are in business. Now, these are the new paper that I have actually put it on I will put it on USB, so you can have access to it. Looked at some SLA violation when you migrate virtual machines for different algorithms. You can see this one is actually the best. The minimizes SLA violation. Again, the same algorithm also minimizes the number of virtual machine migrations. So as you minimize the number of virtual machine migrations, you also minimize the SLA violations. So that's all for me today. Do you have any questions?
In this scenario, actually, the role of broker becomes very important.
Exactly.
Because ultimately, all these things will be decided by the broker.
Exactly. Very, very important. The broker can actually do the service recovery, the discovery, do the negotiation. Very, very important in the federated cloud. Much more important than actually single cloud. Any questions? Yes, ma'am. Huh? You okay? No question? Yeah. You want me to come down? You whisper it in my ear. Okay, we'll do that later. What about girls? You don't ask questions? I know later on you ask me a lot of questions.
Put some light on communication between the hops and the cloud, because the communication aspect is too much involved in that.
In where?
Hop to cloud.
Fog to cloud. I haven't thought of that. So when I think about that, I will let you know. No questions? They are, but it is not actually very reliable because it is done within small clusters. No, the data is out there. I seen the data, the traces, but I haven't seen a big traces that we used for workload distribution analysis. These are just small migrations between small clusters. I will find and send you the location if you want to. But I don't think they are reliable in terms of coming up with acceptable model because they are small. Unless you wanted to take it and then multiply it by a factor of say 2, 3, 10, each one of them, and say you can do that, you are allowed to do that.
One of the important aspects of this SLA validation is the ambiguity that are given in this publications. So can you also model
Publications?
when we publish a particular service,
Yeah.
in the written document there is some ambiguity.
Yeah.
So maybe this functional related ambiguity or the non-functional related ambiguity. So there, I think there may be the one aspect to model that ambiguity. So this is the one major cause of this service SLA violation. That this publisher wants to say some other thing, and I misunderstand or I.
Yeah. So how can you solve that problem?
The one aspect I thought earlier that to find out all the ambiguous word and do the some type of the analysis.
Where we can do that?
Like generally, we write this generally, mostly, 80% is all the ambiguous word.
I don't know how you can actually solve ambiguity. Language is 100% ambiguous. There is 1,000 ways of saying the same thing. Particularly if you are a lawyer, you wanted to actually say it in a way that you just click and say I agreed with it. Unless you digitize the whole thing, where the user is, then if the user if the user chooses a wrong wording again, who is going to be blamed? The system, the service provider, the lawyer? Who? You choose it. So language is, I agree with you, but language is very difficult. Human language is very ambiguous, right? If now I was, the way you say acha, is the way the word is spelled the same way, but the action that goes with it is quite different. How can you remove this ambiguity? Very difficult, right?
Different kind of ambiguities.
Different kinds.
Like what you said is phonetic ambiguity.
Yeah.
Right. There might be semantics.
There is semantic, syntactic, so many of them. So I don't know. I think for
what he means to say is that the agreement SLA should be clearly defined. That is what he means to say.
But it is impossible because it's written by lawyers most of the time, right? So and
see, while downloading any application, do you ever read the terms and conditions?
Yeah.
Never.
I don't think you will read.
When we are not reading those things, we are just signing the agreement.
I don't think you will read.
And I am pretty sure that if you read, you won't sign ever.
No, you will never do anything. Okay.
a simple sim.
Yeah.
Read the whole thing, you will never.
Yeah, even nowadays, you want to buy a train. When we go on the train, we buy what is called some card. It has name. Just to buy that for $6, and then you add money on it. There is 20 pages of this that you need to read and say I agree with it. I agree with it. Nobody reads it. They give you this with on your mobile phone. Nobody reads it. Yes, and then they
not
send
only
you.
that, sir. Even while taking loan from bank,
Yeah.
there is a whole lot of agreement, but
Yeah.
nobody reads even
Nobody
that.
nobody reads. Nobody reads.
You cannot take the loan.
Huh?
You cannot take the loan.
If you read, you can't do anything. Let me tell you. All these mobile phones will not work if you read it. They also know when they design. Don't think that they don't know. They know. They actually discouraging you from reading it. But how are you going to solve that then? Particularly, maybe you can convince me to read it. None of these young girls and boys will read at all because they have better things to do. It's better to watch movie on the mobile phone than reading it, the contract agreement of why they're reading it, why they're watching it. Any other question? Okay. The size of workload flow. In particular, we wanted to make it big and read it from a file. as it is now, it is actually hard-coded in the program. So it's very difficult to simply leave it there. You can actually put it in a spreadsheet if you want to, and transfer it to TXT file and read it from TXT file and populate the array and then simulate for very large workflow. So we will do that tomorrow, but you need to finish the first part. Okay?
Sir, can we use montage workflow? Montage.
Yeah.
Okay.
You can do that.
epigomic montage.
The scientific workflow.
Yeah.
You can do that. Okay, thank you.
So thank you, Professor Jemal, and he is taking a break. Last many days he is talking, and he did a lot, let's say, for us as far as this particular area of the cloud computing is concerned. I'm pretty sure that at the end of the day, you'll be having a good hands-on experience, isn't it?
Yeah.
That I can just feel that the kind of enthusiasm that you have shown in this particular course.
Yeah.
So thank you, sir. You have given a good discourse here, and that we'll do on the last day by felicitating. Right, that we'll be doing it. In the meantime, I thought of, because yesterday I have seen that you developed some sort of enthusiasm in the meta-heuristics.
Yeah.
Yesterday he talked very nicely about the particle swarm optimization. That is a kind of a meta-heuristic which is quite often being used in this particular area of the resource provisioning, cloud resource provisioning, apart from many other areas in which the meta-heuristics, especially particle swarm optimization, that are being used. We have heavily used genetic algorithm as well, and you will find that the GAs are pretty helpful in such a kind of a problem. And yesterday, as we were discussing that you have to first identify the kind of problems. That is, the problem should not be polynomial solvable, otherwise there is no need to apply such kind of meta-heuristics. So first you need to identify that the problem is NP class of problem, NP complete, NP hard kind of a problem. Then only you can look for applying such kind of meta-heuristics. So genetic algorithm is one of them, and I thought of giving you improved genetic, because just fine tuning here and there, you will find that a new version, a new variant of GA is there. That is what I did. I means we did, along with my student, and this kind of technique has been developed, which has been thereafter have been used by many of the researchers in this particular area. So I would like to deliberate upon, and then little diverging from the cloud resource provisioning to another area of the mobile computing. And the channel allocation is a very let's say thrust area, because the channels are scarce and the users are increasing day by day. In the mobile computing, mobile communication area, the channels are limited, the frequency band is limited, and the users are increasing. So how, and in fact here also we do find, in his resource provisioning model, he has considered how the channel or how the network can impose the delay. So that particular area we have applied this improved genetic algorithm. So I will be discussing upon, starting from the genetic algorithm, the basics of the genetic algorithm, so that you can just think, as yesterday he discussed about the PSO, the basics of the PSO, right? So we will be discussing about the basics of the genetic algorithm, how the genetic algorithm can be applied in general, so that you can develop an idea to apply for your problem, right? And then what kind of let's say modifications we have made to this particular GA, so that it became a little elite. We call it elitist, right? So how it became by applying some fine tuning here and there, so that it can be applied to suit your problem, right? So I will be discussing all these. Of course, I just have listed this. The idea has been published in this particular paper long back. So long back, it is a 2006 paper with one of my students, right, in IEEE transaction. But the same idea is being applied in many other disciplines as well. So that is why this publication is a little older one, but not, the technique is not old. So then you can think of applying this particular one. So now to discuss about the genetic algorithm. Like yesterday he discussed about the particle swarm optimization. he said that how the bird moves, actually that is the phenomena derived from the swarm. And here the genetic algorithm, as the name itself suggests, it has been derived from the genetic inheritance from the ancestors. So as you know, we inherit many of the genes of the ancestors, and these evolves also. That is what the Darwin theory is. Darwin theory is in fact says the survival of the fittest. So the whole genetic algorithm is based on this particular principle of the survival of the fittest. So we'll be discussing about this. First, let us see that what I said, that there are many problems for which we do not have the fast. As he said, that it's a big search space of the solutions. A huge number of solutions are there, and not all the solutions are good. So we do have to find out one which is good solution. Of course, we cannot say here it is the best solution, but of course we can be closer to the best solution, right? We can be very close to the good solution. That is where we do apply these kind of techniques. So you see that many problems are there for which we don't have, and these problems actually, when we foresee and when we look at this particular problem, these are again the NP class of problem. You have to just consider this particular fact in mind. And any problem, as we see, that can be perceived as a search through a space of potential solution. You have a big search space and you have to go through one by one, let's say performing a linear search, that which one is the good solution. But then linear search, if the search space is very big, consumes a huge amount of time, right? And then you cannot go one by one and can check which solution is the good solution. So linear searching is strictly prohibited for such kind of a search space. So you have a big search space, and as we said that the objective is of course the best solution. We look for the best solution only. So our objective is that we must achieve the best solution. As far as the whole search space is concerned, we are looking for the best solution. And as we said that the search space is small, then we can perform the exhaustive search, like we can go one by one and can check. Linear search, usually we can apply the linear search if the search space is small enough. But if the search space is big enough, then obviously we cannot apply this technique. We do have to resort to the artificial intelligence techniques, and these meta heuristic is actually the AI techniques, right? These meta heuristics are the AI techniques. GA is one such technique which is highly based on the random searching, right? And that is why it's said to be the stochastic algorithm, right? This is a class of algorithm we call as the stochastic algorithm, which is based on the natural phenomena. So natural phenomena, as I already said, genes are there, we inherit the property of our ancestors, right? That is what the philosophy behind the genetic algorithm is. You will find that I have discussed one of the example of the rabbits and foxes. It's a very good example. I will will try to give you a sort of a short story about this particular rabbit and foxes. And as I said, the Darwin's theory is the survival of the fittest. As you know that the one who is dumb is not likely to survive, and you have to be smart. Even among ourselves also, we feel that if we are little calm, little cooler, then probably the people will catch hold of you and will proceed. So you see that we have to be smarter. That is what the Darwin theory says. In order to survive in this particular world, one has to be smarter, and you are smart enough, that I understand, right? So in order to do that, in fact, one has to be. That is what the Darwin theory is. And this particular example suits this best, rabbits and foxes. And the story is like this. At a time, there was the population of rabbits and there is the population of the foxes. Okay. So you see that the rabbits are likely to be eaten by the foxes, because the foxes usually catch hold of the rabbits and eat them up. So in order to survive, rabbits have to move faster. That is, the rabbits have to be smarter, isn't it, in order to survive. Otherwise they won't survive. All the foxes will catch hold of all the rabbits in the forest, and there will be extinction of the rabbits eventually, right? But in order to survive, they have to move fast. But there are some rabbits which are dumb, they cannot move very fast. They are likely to be eaten by the foxes, right? The foxes will easily catch hold of those rabbits, right? And of course they won't be able to survive. So you see that then the natural phenomena goes. What happens in the nature is that the rabbits mate and reproduce the children, right? The mating process goes on and the children are reproduced, right? So there is the possibility that the smart rabbit is mating with the smart rabbit. So smart rabbit smartness is because they possess the genes. They possess such a type of biological genes, and that is why they are smarter. You know that our characteristics are determined by the genes that we carry, isn't it? That the genes we carry. So the smarter rabbits are having the better genes. So smart rabbit mating with the smart rabbit, and the genes it mixes with each other, and the descendants are the reproduced children will possess these kind of genes. Right, the smarter genes, you can say. You can just say in the layman term, these smarter genes. So smart rabbit mating with the smart rabbit, it is likely that the reproduction or the descendant will also be smarter. Right? Smarter rabbit mating with the smart. There is possibility that the smarter rabbit is mating with the dumb rabbit also. Right? So you can say 50-50 possibility is there. Some smart genes, some bad genes. Right? Or maybe all smart genes also, it happens. You might have seen many a times that the smarter parents are generating good children. Sometimes the smarter parents are not able to, the children are dumb. That is also the possibility. Right? And that why happens, that also we'll see here. Right? So the possibility is more likely, and that is why I say possibility, because it's a highly stochastic phenomenon. Right? So you see that the smarter rabbit is mating with the smarter rabbit. Probability is that the smarter descendants will be generated. Smart rabbit mating with dumb rabbit is a 50-50 kind of a possibility. Then dumb rabbit mating with dumb rabbits. Obviously, the more likely chance is that the dumb rabbits will be produced. Right? And if it is a dumb rabbit, obviously it will be eaten by the foxes. So the foxes, they are doing their job. Right? Likely to catch hold of the rabbits and eat them up. Right? So you see that at some period of time you will find that the smarter rabbit, the chances of survival of the smarter rabbit is much more, because they are less likely to be eaten by the foxes. Right? So that we will have let's say at some period of time we will have the good population of the smarter rabbits, and then you see that if there is a good population of the smarter rabbits, maybe after some time it will happen that the population of the rabbit became so smart that even they are catching hold of the foxes and eating them up. But it never happens, you know that, because the same phenomena goes in foxes also. Right, the same phenomena, this goes in foxes also. This is the whole sort of a nature. Right, so even the human being also, you might have seen that our children are much smarter than us. So in the beginning itself, and the internet of things kind of a thing which is going on, the child is born with the internet, isn't it? There is a very good advertisement from MTS sometimes back. Dr. Zahid has given me that particular clip. The child which is born immediately starts using internet. So that kind of child we are producing now. Right? Immediately starts using the internet. So you see that. So what is happening actually is that the smarter generation is coming up. But let's see in the nature, all are getting smarter. It is not that only human being or only the rabbits or only, so all are getting smarter, because the same phenomena is being repeated in all the species that we have on the earth. Right? So this is the idea behind the genetic algorithm. The basic idea behind the genetic algorithm is that the two parent, they mate, they reproduce the children. Right? When we are talking the parent will be mapped with the solutions. Eventually, we call it chromosome in terms of the genetic algorithm. Right? We call it the chromosomes. So the two chromosomes are mating with each other and let's say reproducing the children. Another solution, you can say. Two solutions producing another solution. Possibility is that you have the good solution at the beginning itself, you have the good population of the solution, let's say. Then the possibility is that you will have better solution at the end. Right? So this is the whole idea behind the genetic algorithm. We can deal it threadbare, the genetic algorithm, how in fact the problem is converted in these kind of solutions, right, that we'll be dealing with. And of course I have written some of the words from the biology, but probably you may not be interested in these terms. Most of the terminology that we use in the genetic algorithm has been derived from the same life science, biological sciences. Like we use genotype, phenotype, etc., etc. These are the terms probably you will encounter when you are using genetic algorithm, right, when you are applying a genetic algorithm. Every gene controls the inheritance of the character. As I told you, you know that our characteristics are defined by the genes that we carry, right? By the genes that we carry. So you see that here also you'll find that a solution is there which consists of the genes, and these genes will define the characteristic of the solution that you have obtained, right? The characteristics of the solutions that we have obtained, whatever the problem is, right? Whatever the problem is, solution will be obtained in terms of the genetic algorithm in form of the chromosome, and this chromosome will consist of the genes, and each gene will in fact control the characteristics or derive the characteristics, define the characteristic of the solution. Of course, there are 46 chromosomes in human being, man, and which derives its features, characters, etc. We are not interested in that. Objective is exploiting the best solution and exploring the search space. Right? This is what the objective is. We do have to explore the big search space and exploit the good solution. Right? These two phenomena which we normally carry as far as the searching the solution is concerned, exploiting and exploring. Right? So both exploitation and exploration, it will be carried forward together in unison in this particular genetic algorithm. Here the chromosome that we are calling, in fact each chromosome represents a potential solution to the problem. So any problem which is given in hand, we do have to define the chromosome corresponding to that particular problem, and that chromosome is nothing but the solution to the problem, right? That is the solution to the problem. So then you can say that we do have to start with the solutions, right? Here we do have to start with the solutions, and you start with the solution, some random solutions we can start with, may not be good solution, right? But then we are aiming that over the period of time or over the generations or over the iteration, we get the good solution, we get the best solution rather, right? That is what the aim is. Of course, written is that GA is a good balance between the exploitation and exploration. Of course, we took it as the hill climbing and the random search, but GA is factually the let's say good mix of the random search as well as the hill climbing, which is the exploitation and exploration. So both these exploitation and exploration are well applied in genetic algorithm, right? Multi-directional search space successfully applied to various optimization problems. So not only the cloud resource provisioning, probably which Professor Jemal and many of us have applied thoroughly. In grid computing we did apply a lot. We did apply this particular one, genetic algorithm, a lot. Many of my students probably sitting here also, right, will find that they have applied. But there are many other fields also, like wire routing, scheduling, adaptive control, game playing, cognitive modeling, transportation problem. TSP is one of the problem in which all sorts of these soft computing techniques are applied and they are tested with. Of course, we can take an example of TSP eventually, that how the TSP can be modeled using the genetic algorithm, right? And of course, there are many other problems, mobile communication also. And in fact, this particular discussion will be over the channel allocation problem of the mobile computing eventually. Going with what exactly the genetic algorithm is, a very brief flowchart for the simple genetic algorithm, right? For the simplest genetic algorithm is like this. You start with generating the random population. So in fact, we start with generating the solution, as I told you. We start with generating the random population. So generate a random population, right? Random population of the solution. Thereafter, you score the population. Scoring the population is testing the population whether it is good or bad. Scoring means this: you use a fitness function, right? As happens in the particle swarm optimization, also yesterday discussed. There might be many sort of a fitness function. What the objective is? Actually, the fitness function depends upon what our objective is, what we are trying to achieve by this particular solution, right? So we can score the population using the fitness function, right? And then of course generation count is incremented because you do have to go through number of generations. So increment the generation count, and if you are able to get the acceptable solution, then we can stop and can say that okay, we are successful in achieving the good solution, right? Otherwise, if you have reached maximum number of generation, then probably you could not get the solution, but the total generation that you have to go through has reached, then probably we can terminate thereafter, right? So reached maximum number of generation, and then if not so, then these are the operations that actually the GA operations, right? These are the two operations actually which we call as the GA operation: selection for reproduction, selecting the parent out of the good number of chromosomes or good number of solutions in the search space, you have to select the parent also that are going to mate, right? You have to select some of the chromosomes that are going to mate. So selection is one, and then performing the crossover and mutation, that we have written as the create new population via recombination and mutation. Recombination means just mixing the genes of the two parent. Usually we call it in the genetic algorithm as the crossover operation, right? The crossover operation is in fact mixing the genes of the two parent, right? So these two operation, mutation of course, which is randomly flipping some of the genes, that is the operation which we call as the mutation operation, right? So these are the operations that we do have to apply. In terms of the code, the simple genetic algorithm comes like this. Population initialization, we do have to start with the population, some sort of a population corresponding to the problem. Then population evaluation, scoring the population, and then these are the steps which we do have to apply repeatedly. That is the until solution converges, right? So the convergence of the solution can be achieved by, let's say, observing the fitness of the population, that over the generation it is not improving, so you can say that the solution has converged, or you have reached maximum number of generations, or whatever the termination criteria we wish to apply, we can, right? So until solution converges do, and then we do have to perform these operations, that is perform crossover and mutation, evaluate the population, and reproduction, that is the selection process will carry on. We do have to repeat these steps until you get the good solution, right? That is what the objective is. So if you have any problem, again I'll like Professor Jemal, I can ask any problem so far. We can interact with, let's say, in this particular fashion. If you have not understood so far anything, that we can interact, that we can always explore. So any time in between also you can put your questions, right?
Sir, what is that stochastic means that?
Stochastic means randomly. You do have to apply the random. We'll see that. Eventually we'll see that so these, actually the whole phenomena depends upon the randomization, right? So it's a high used of the random numbers. You will find it, right? We'll come to that particular one. Anything else? Nothing. So as far as the initial population is concerned, how to generate the initial population, how to design the chromosome. So given a population, let's consider the cloud resource provisioning problem. How this cloud resource provisioning problem can be converted in terms of the solutions. That is in fact generating the chromosomes. So the objective, the very first problem when we are going to apply the genetic algorithm is to convert our problem in terms of these chromosomes, right? So the very first problem is this, and for that there are number of techniques that we can apply, right? There are number of techniques. Like I said, that the chromosomes or the GA population can be represented in terms of the bit strings. In fact, when the GA was proposed, the most sought after population generation was the using the bit strings. That is use 01, 01, 01. So it's not that it's a 01, 01. It has some meaning. It has some significance. How to have the population in terms of the binary bits 01, etc. Right? So this is one of the method. I'll discuss. I hope that I'll be covering up the traveling salesperson problem, and then you'll find how this 01 can be for traveling TSP problem, and then that can give you the idea that how your problem can be converted in terms of the binaries, right? So let's say it can be in form of the bit strings. It can be in form of real numbers also, depending upon the problem, for which we are going to apply the GA, right? It can be in terms of the real numbers. It can be permutation of elements as well. Again, I said, depending upon the problem. It can be the list of rules also, if you are applying it for logical programming sort of thing, right? It can be list of rules, or it can be any data structure that suits. That is why I have written any data structure. So now the data structure is to be decided by you only. That this is the problem, what kind of data structure will suit to your problem, right? So the data structure for the initial population generation is to be decided by the one who is going to apply it, right? As far as the crossover operation is concerned, as I told you, the two parent, you do have to find the two parent which are going to mate, so that the reproduction the children can be generated, right? So just consider the crossover operation, pictorially, here you will find that the parent A all green. So this represents the characteristic of the parent A, right? The genes that the parent A carries, all green. Then the parent B is all pink, let's say. And then after applying the crossover operation, the offspring has been generated, which contains some green, some pink. So it means the mixing has been done. Mixing of the genes have been done. Right? This means that the mixing of the genes have been done in generating the children. You can just consider that you have two sort of liquid, one with green color, another with blue color, let's say. Mix it up so that the new liquid is having some blue, some green sort of a thing. Right? So this way, now the offspring is having the characteristic of both the parent now. And that is what happens also in the nature. No? We are supposed to have the characteristic of both the parent. Of course, sometimes mutation also occurs, and as I discussed, that sometimes it happens that even a very good parent having a very naughty child. So that also is possible, because it has, as I said, stochastic randomness is there. Sometimes the mutation took place and suddenly one gene altered the whole characteristic of the individual. Right? It happens. Mutation occurs. Right? So that is possible. So this is the operation which is in fact the main operation of the genetic algorithm, the crossover operation. Now the crossover operation. Of course, there are many types of crossover. I just have listed very few here. But going through literature, we will find that a huge number of crossover techniques are available in the literature. A very good number of crossover techniques. Most applied crossover technique is one-point crossover, where you select a crossover site of the two parent. Right? Just consider the very first figure in which you have first parent having all zeros, the next parent is having all ones, and then you select a crossover site randomly. Select a crossover site randomly, and then just mix the genes of the two parents from the crossover site. From the crossover site, mix the genes of the two parents. Right? So you see that the children, first children is having from first parent zeros, and thereafter rest of the bits from the second parent. So first few zeros, thereafter all ones. Similarly, the second children is vice versa. Right? That is, it is containing the few ones, thereafter all zeros of the first parent. So the two children have been generated with the two parents, let's say. Right? The two children have been generated that are possessing the characteristic of both the parents. This is what the crossover operation is, and this is one-point crossover. Right? This is one-point crossover, selecting just one site for the crossover. Is it okay? Similarly, as we selected one site, we may select n sites, let's say. If the chromosome is big enough, then we do have the possibility of selecting n sites. Right? Like in this one we selected 3. You can have 2, you can have 3, you can have 4, depending upon how long the chromosome is. And of course, how to decide on how many sites to be selected. Of course, this also depends on the problem that you have. This depends on, let's say, performing experimentation also, that which kind of crossover will suit us. Right? So you see that selecting 3 sites, then you do have the possibility of flipping from one parent to another, then after that you can just change it. I hope you are getting it. Right? So this is how we apply the crossover operation. There are many kind of a crossover, like there are cyclic crossover, ordered crossover, so many types of crossover are available in the literature. The uniform crossover is one which depends on a masking vector. So which genes of the first parent is to be selected will be decided by the masking vector. So you do have a masking vector corresponding to the size of the chromosome. Are you getting this? We have a masking vector corresponding to the size of the chromosome that will decide which genes of which parent will be taken for the children, will be carried forward for the children. Right? So this is how we apply the uniform crossover. Right? So just few crossover techniques we discussed, but in fact there are many. As far as the mutation is concerned, I already told you, depending upon how often and where you apply the mutation, you can just alter. So for mutation, we don't require 2 parents. Just one chromosome is good enough, and we do have to flip some of the bits. right? Just make 1 to 0, 0 to 1 like this, and the mutation will be performed. You will have a new solution, right? This is how do you apply the mutation. Okay, like here you have just sort of a, after crossover you have this, after mutation you got some of the bits have been flipped, right? Some of the bits just flip it up, and then you have altogether a new children after applying the mutation. Now as the fitness is concerned, we do have to decide on the fitness also. Like for most of the grid scheduling problem, we normally look for the make span. We do have to optimize the make span. Sometimes we do have to optimize the let's say the turnaround completion time. We do have to optimize the completion time, response time, or many other factors. Even you can optimize the reliability also. You can optimize so many other. So you do have to decide what should be the fitness function, what you are looking to optimize out of the problem. Like for a mobile computing problem, channel allocation especially, we are optimizing that the call drop call block should be minimum. So that becomes the fitness function, right? While you are making a call, there should not be call drop. While you are establishing a call, the call should not be blocked, right? So this blocking, dropping, etc. depends upon the domain on which we are going to apply the genetic algorithm. So the fitness function is to be decided, and this is very important to choose a fitness function, to decide the fitness function when you are going to apply these kind of techniques there. As far as the selection is concerned, chromosome selection, that is to find it out which of the parent will be selected to undergo the crossover and mutation. Right, that particular technique is said to be the selection in the genetic algorithm. We do have to apply the selection method. Are you getting this? That how do we select the parent? As we said that we do have to be smarter. We have to be smarter. We do have to find the good parent, because there are more chances that the good parent will produce good children. So we do have to select, and the process which we apply to select the parent that will undergo the crossover mutation for reproduction, in fact, is known as the selection process, right? So you see that, and in fact there are many selection processes, selection methods available again in the literature of genetic algorithm. There are many selection methods. I just have listed a few of them. Like the well-known selection method is Rowlett-Weil selection method. Right, this is a well-known selection method that is quite often applied for genetic GA problems. Rowlett-Weil selection method, then of course there are Boltzmann selection. Sometimes you do have to apply this. Tournament selection, rank selection, ranking using the ranking also of the population. We do apply the selection. Steady state selection, and the list is never ending rather. So a good number of selection methods are available. We can deliberate just one, which is the Rowlett-Weil selection, quite often applied for the GA problems. In fact, we do have applied quite most often this Rowlett-Weil selection method. Now to consider the Rowlett-Weil selection method, just consider this. In fact, the Rowlett-Weil, the name has been derived from this wheel of fortune, where you just rotate the wheel, and if it let's say stops before the arrow, and probably the arrow is pointing you, then you will be selected, something like this. So the stopping of the wheel before a arrow is more dependent upon the area that the wheel is containing, right? So more area has more probability of stopping before the arrow. This is the idea behind this Rowlett-Weil selection method. You just consider how this particular selection method is applied. So this particular example considers four chromosomes, right? And all these chromosomes are having their fitness being depicted by the area in the wheel. Like the one which is having the larger portion is having the larger fitness, right? The one which is having the larger area, covering the larger area in this particular wheel, is having the larger fitness. So depending upon that, depending upon the fitness, the whole wheel has been divided into the areas, right? So now just consider that we do have considered 4 chromosomes here. What we do first, we just sum it up, all the let's say the fitnesses have the cumulative fitness, right? Just have the cumulative fitness, and let's say this cumulative fitness is capital S, right? This cumulative fitness is this capital S, Okay, and thereafter you generate a random number between 0 and S, right? The least fitness is 0 and the biggest fitness that we have, cumulative fitness, is S. So we can generate a random number between 0 and S. Let's say it is R. Then go through the population and sum the fitnesses from 0. So now you make 0 plus R, right? You do 0 plus R. R is a random number which has been generated between 0 to S. 0 plus R will give you a value. Go with the first chromosome. If it is having the fitness more than R, then you can leave that. Add the fitness of the second chromosome in this 0 plus R, right? If it is now becoming more than that, then we can select that particular chromosome. I hope you are getting. If not so, then I have another, let's say, example, the same for the selection method, this Rowlett-Weil selection method. In this, we considered 8 chromosomes, right from 1 to 8. 8 chromosomes we have considered, and this red numbers, they are actually the fitness of the chromosome, fitness of the each individual chromosomes, right? If you sum it up, you will find total 18. So cumulative fitness is 18, right? The cumulative fitness is 18. So what we did, we generated a random number between 0 and 18 here, and let's say the random number generated is 7, right? Random number generated is 7. Then you start with the first population. The fitness is 1, which is less than 7, so you can omit it. Go with the next one, 2 plus 1, which becomes 3. 3 is still less than 7, so you just do away with this, right? Then add 3 also, so 3 plus 3, now it is 6, which is still less than 7, right? Just discard it. Then add the next one, which is 1, so now total is 7 now, and random number generated is also 7, so we can select this particular one, right? This is what the selection method is. Just select this one. So this way we can select, we have selected one of the parent. Similarly, we can select another parent by generating another random number between 0 and 18. Let's say it is 12, and going through the same logic, we will find that the next parent to be selected will be the parent number 6. So you have selected first parent, second parent, selection process is over, and then use this parent to go for the crossover and mutation, right? So this is the selection method, and especially the Rowlett-Weil selection method, right? The one which we have considered here. But as I told you, there are many selection methods that we can, right, that we can think of. And in fact, it depends again on the problem, what kind of selection method will suit us, right? Now, to consider an example of the traveling salesperson problem. I hope that you all are aware of the traveling salesperson problem, right? You all know about the TSP, right? So TSP problem is actually the problem in which a traveling salesperson starts from a city, traverses all the cities exactly once. Don't have to repeat this. So probably you know about the, and in fact he has to come back to the city from which he started. TSP is one such problem which is an NP hard problem, right? And any let's say evolutionary techniques or any meta heuristics that is developed is applied on TSP, and you just apply it on TSP, publish a paper if it is a new meta heuristic technique, right? You just apply on TSP, publish a paper. Because the TSP is a known hard NP hard problem, right? So you just see the TSP and how the GA has been applied to TSP, right? So as I told you, TSP is one in which you start from one city, traverse all the cities exactly once. So like you know the Hamiltonian circuit, to obtain the Hamiltonian circuit, given a graph, you do have to start from one vertex, go through all the vertices exactly once, right, and come back to the original vertex. So a circuit has been completed in which none of the vertices are being repeated except the start vertex. That is known as the Hamiltonian circuit. In fact, the TSP problem is obtaining a Hamiltonian circuit from a graph, from a given graph, right? And in fact, if you consider that the graph is a complete graph, then there are many possibilities, many Hamiltonian circuits are possible. There are many Hamiltonian circuits possible if a graph is a complete graph. I hope you understand about the complete graph. Yes. Complete graph is one in which all the vertices are connected with all other vertices. Direct connection, just with one edge. The vertices are connected. This is what the complete graph is. Okay. So let's say if you fix the start vertex, that is the headquarter in terms of the traveling salesperson. If you just fix the start vertex out of n cities or out of n vertices in a complete graph, right? Start with the first city, go to the second, then go to the third, go to the fourth. Don't have to repeat the vertices. How many such combinations will be possible?
n into n minus 1 upon 2. N into n minus 1 upon 2.
N into n minus 1 upon 2. These are the number of edges that you are talking. How many such circuits will be possible? It will be factorial n. Factorial n minus 1. Because the first vertex you already have chosen. If you don't choose the first vertex, then it is factorial n. But if you have already chosen the first vertex, it is factorial n minus 1. Why? You see that you start from the first vertex. How many possibilities are there? N minus 1. Once you take one, decide on one, reach to that one, another possibility which remains because you cannot go to the first vertex, another possibility is n minus 2. Then go to the second one, n minus 3. So multiply all these, it becomes factorial n minus 1. Right? So the total possibility is factorial n minus 1. And I am telling you that is because of this only this particular problem, the TSP problem is NP-hard problem. Right? Factorial n minus 1. You can just think of, let's say if there are 4 cities. If there are 4 cities, so the total possibility is factorial 3. Factorial 3 is how much? 6. So out of 6 circuits, you have to choose one which is the best circuit. So best is again in which terms? You do have to decide on the fitness also, fitness function. So best is in terms of the, let's say the cost incurred, maybe the distance traveled. From one city to another city there is some distance. From second to third there is some distance. Right? So we can decide on the fitness function by the total distance traveled by the traveling salesperson. This is to be minimized, no? This is to be minimized. So you can say that the problem is the minimization problem, optimization problem, in which we do have to minimize the fitness. Right? So we do have to minimize the fitness. Okay. This can be for traveling salesperson if the company is sponsoring the salesperson. This can be the pricing also, the cost. Let's say he says that you go from one to traverse all the cities. Don't spend too much, he says. Obviously, the traveling salesperson will think that the city is not to be repeated. And from one city to another city, how much money is involved? Then the second to third, how much money is involved? Add all this money, this is the total cost incurred on the tour. This is to be minimized. So any fitness function we can choose. Right? For the TSP problem, any fitness function we can choose. Right? So the whole problem is like this. So we said that if there are 4 vertices, the total possibility is 6. If there are 5 vertices, the total possibility will be 24. So let's say out of 24, if you have to find one which is the best path, then linear search can be performed. No problem. So far seems that the TSP is not an NP-hard problem. 24 is nothing, no? We can easily perform the linear search and can find it out that which one is the best solution. But just consider that there are 50 cities. Factorial 49. Can you calculate what is the value of the factorial 49? It's a so large a value that even the fastest machine may take a week to compute which one is the best one. Right? So that is how you see asymptotically how the time grows. Right? And that is why the traveling TSP problem is an NP-hard problem. Right? So TSP problem is an NP-hard problem. Are you getting this? So total out of factorial 49, we have to choose one which is the best solution. And if you do the linear search, go one by one to see that whether it is good, whether it is good, whether it's, we'll end up with sometimes a week or so to get this is the good solution. Right? And then in fact, that is why you see that the TSP is most sought after if you develop a new technique, meta-heuristic, new meta-heuristic. You apply it on the TSP. TSP is well known NP-hard problem. Right? You apply it on the TSP and then find it out how much time you take with your technique to converge the solution and what is the quality of the solution, the fitness of the solution that you have produced. Right? So you see that now how we can apply the genetic algorithm on TSP. Right? Let us see how we can apply the genetic algorithm on TSP, and for that, here you come to this particular point which says that decide on the chromosome now. What type of chromosome we have to decide, we have to choose for the TSP problem, right, while applying the genetic algorithm. So we have the possibility of choosing either integer or the binary, right. We have the, let's say, either we can design the chromosome in terms of the 1010 binaries, or we can have 2, 3, 4, 5, something like this in terms of the integers, right. Now if we, let's say, go with the binaries, what happens? If we go with the binaries, then if binary, then each city should be coded as a string of log n. That is, if there are, let's say, 5 cities, how many bits are required to represent the 5 cities? 3, right, 3 bits. Even 6 cities, 3 bits. Up to 8 cities, 3 bits will be sufficing. Above 8, it becomes 4 bits, right, and that is why we have taken log n. For n cities, it is log n with the ceiling function, right, because for 5 also you require 3, for 6 also you require 3. So with this log n with ceiling, so now one city will be represented with log n, right, one city will be represented with log n. Okay, for n cities how many bits are required? Because the traveling or this whole tour will be represented by one city, then next city, then third city, then fourth city, and so on. So if you have n cities, the total number of bits will be how much? N into log n, right, the total number of bits will be n into log n. Are you getting this?
Yes.
So now you see that when the n increases, the total number of bits will increase, right, as n increases, the total number of bits in the chromosome will increase, right. And not only that, if you have, let's say, 8 cities, then no problem, but let's say if you have 5 cities and you have represented the cities as, let's say, 0, 0, 0, then 0, 1, 0, 0, 0, 1, 0, 1, 0, and so on, then after performing the crossover, maybe some cities which are produced are in fact invalid cities. That is, some becomes 110, which is non-existent, right. So this is the problem while applying the, let's say, while decoding the TSP problem in terms of the binaries. Integers are much easier. Let's say if you represent the city as city 1, 2, 3, 4, 5, right. So one of the tour can be represented as 1, 2, 3, 4, 5. Another can be 2, 3, 5, 4, 1. Of course, none of these integers are to be repeated because the cities are not to be traversed again, right. Then it is short enough, number one. Moreover, after applying the crossover, etc., the invalid city will not be produced. So it is better to apply the integer representation, right. It is better to, in fact, we can apply the, let's say, the binaries also, but the drawback with the binary is, number one, the length will be too much. Number two, invalid city. Invalid can be corrected also, because it happens in the genetic algorithm that sometimes you do have to apply the repair mechanism also. After crossover, etc., one has to apply the repair mechanism also. But let's say that integer works very fine. So we can let's say go with the integer representation, right? Of course, clearly we require some repair algorithm. Integer representation is better in this particular situation. The integer representation is better, and then for n cities, one of the representation can be I1, I2, I2, and so on up to In. This can be one of the tour. Are you getting this? Right? So this way now we can generate many tours initially, and we can call it as the initial population in the genetic algorithm. Right? We can generate such many tours, and we can call it as the initial population of the genetic algorithm of this particular problem. So let's say one of the tour is 1, 2, 3, 4, 5, 6 for 12 cities. One of the tour or one of the population, one of the chromosome is like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, straightforward. Randomly you do have to generate, just keeping in mind that none of the cities are to be repeated. So none of these values, integer values, are to be repeated. They represent the city in fact. Let's say this is 1, another is 7, 3, 1, 11, 4, the other one, this one, right? The another chromosome is this. right? So these, let's say 2 parents randomly generated. Then you apply the crossover. For applying the crossover, you can use any of the techniques. In fact, here we have used, let's say, which one? This ordered crossover, OX operator. This is also a type of a crossover operation. Ordered crossover. Ordered crossover is one in which, after selecting the crossover site, you of course exchange, but you maintain the order of the cities while exchanging. Right? We maintain the order of the cities or order of the bits. That is known as the ordered crossover. Right? So let's say we applied the ordered crossover, applied this on on these two. This one of the parent, this is another parent. Chosen part is 4, 5, 6, 7. That is here from you choose. So just exchange this in the 2 parents. You will get a new chromosome. You got a new chromosome after applying the ordered crossover. Now this particular chromosome will possess certain property in terms of the fitness. So again you can test the fitness. How to test the fitness? So from 1 to 11, what is the cost? From 11 to 12, what is the cost? Add it up, you get the cost, the total cost. Just summation, I is equal to 1 to number of cities, the cost incurred on one tour. That's all. Right? You get the total cost of the tour. Okay. So this is one on which you can apply the TSP problem. And in fact, we do have applied for, let's say, while testing this improved genetic algorithm, we have applied it on the function optimization problem also. But I would like to skip this one, the function optimization, where we have chosen a function of the 2 variables, let's say f, x1, x2 here, right? And the function is like this. This is the function. The problem is to optimize the function. We do have to optimize the function with the constant that the value of x1 is between -3 to 12.1. The value of x1 is in between -3 to 12.1. The value of x2 is between 4.1 to 5.8. So now you see between 4.1 to 5.8 you have number of values possible. So for which value of the x1 and for which value of the x2 the function will be maximized. The problem is this. Right? The problem is this. And for that we do have applied the genetic algorithm. Right? We have chosen the binary representation, and in fact I can deal with this and can tell you that how the genetic algorithm, how this particular problem has been converted in terms of the GA, in terms of the genetic algorithm. So you see that what we have considered is that the total population size is 20. Probability of applying the crossover is this, and probability of applying the mutation is this. So how often we apply the crossover and how often we apply the mutation, right? Here is the probability. Now to decide on the chromosome, right? To decide on the chromosome, what we did, the domain of X has length 15.1. X1, sorry, it is not X. The domain of X1 has length 15.1. -3 to 12.1, there is total 15.1, gap of 15.1. So the domain of X1 has total length 15.1. So precision implies -3 to 12.1 should be divided into 15.1 to 10,000. Why? Because we require the functional value up to 4 decimal places. The value that we wish to optimize, we want to be precise up to 4 decimal places. Are you getting this? Yeah. For that only we took that the domain between -3 to 12.1, which is 15.1, is to be multiplied by 10,000. Are you getting this? And this is to be divided in equal size ranges. Now, to 15.1 multiplied by 10,000, which is 151000, right? Which is 151000, will occupy the bits between 2 to the power 17 and 2 to the power 18. The total bits that we require to represent this particular number, right, is between 2 to the power 17 and 2 to the power 18. So that means for the first part, that is for x1, we can have 18 bits, right? For the first part we can have 18 bits. Is it okay? Going by the same logic, we can take the x2. So x2 ranges between domain of x2 is between 4.1 to 5.8, which is, you can just subtract 5.8 with 4.1, multiplied with 10,000. You can just determine how many bits are required for the second part. which is in fact 15 bits. So now the 18 bits for x1, 15 bits for x2. Total 18 plus 15, 33. So total 33 bits will represent one solution, one chromosome. Right? Total 33 bits will represent one solution. First 18 bit will correspond to x1, remaining 15 bit will correspond to x2. So now any population or any children or any chromosome generated this way, we can take the first 18 bit, can convert it into x1, remaining 15 bit, convert it to x2, apply it on function and test what is the value of the function for this particular chromosome. That is how to obtain, how to score the population, how to get the fitness value of that particular population. I hope you are getting it, right? So the total length of chromosome is this. Now you see that one of the solution is this one, randomly generated solution is this. First 18 bit correspond to the value of x1, which can be obtained, x1 can be obtained -3, because -3 is the starting domain value, right? -3 plus the decimal corresponding to these 18 bits, first 18 bits multiplied by 12.1 minus, that is the domain, divided by the total number of bits that we have. Right? This gives you a value which is 1.052426, the value of x1 corresponding to the first 18 bit. Similarly, we can obtain the value of x2 corresponding to remaining 15 bits. Right? We can obtain the value of x2 corresponding to remaining 15 bit. Put these two values x1 and x2 in this particular function which we have earlier shown, fitness function. Put these values in the fitness function corresponding to x1, x2 is this. Put this and you obtain the fitness corresponding to these x1, x2 is this. This is the fitness value corresponding to the x1, x2. Randomly generated x1, x2. Right? Randomly generated x1, x2. So this is one of the solution. May not be good solution. Right? May not be good solution. In fact, out of many such solution, we do have to find the good solution. For that, you just apply the crossover mutation, generate the children, go through the population at a particular period of time. You have some good solutions. You can retain those solutions, etc., etc. Can proceed with the good solutions further. This is what the total genetic algorithm is. Right? Like you see that here randomly generated some 20 populations. Randomly generated. With some 10 here, you can generate it randomly. All are valid. Right? Just randomly generate the solution corresponding. So let's say V1 to V20, 20 solutions have been generated. Right? Evaluate the V1, each of these V's. Evaluate all these V's. Apply the selection operator. In fact, the selection has been applied. Evaluation of all these V's have been done, which are having the different values as you look over these. These are having the different values corresponding to the same mathematical function which we have used. Right? And then, in fact, you will find that we have applied the same, which we discussed, the selection, Rowlett-Wheel selection method. The Rowlett-Wheel selection method, cumulative sum, cumulative fitness, generate a random number, then go proceed with and then find out the sum of the parents which we can use for the next generation, for the reproduction, etc., etc. Right? And in fact, we already discussed what is the probability of crossover and mutation. Of course, the best chromosome has been obtained just going through straight to this particular one. At 396th generation iteration, we find the best value, which is this. Right? So we got the best value at the 396th generation of the applying the genetic algorithm. Okay? So this is just two examples we considered. One is the TSP, another is this. And now coming to the channel allocation problem. Right? And where we tweaked with this genetic algorithm. What kind of a techniques that we have. Of course, genetic algorithm for task scheduling. Professor Jemal knows that we do have applied with many of our students here. They know that we do have applied GA. A whole lot of GA has been applied for the task scheduling problem with the fitness as the turnaround time, reliability and so on. So many fitnesses we have used. Right? Not deliberating with this. Coming to the channel allocation problem. Probably it's a domain which has not been dealt here because it's an entirely different domain, the channel allocation. The problem of the channel allocation is to allocate the channels, that is the frequency band that when we use the mobile phone, we need to have a channel for establishing the communication between the source and the destination. Right? You require a channel. Right? So the channel allocation problem is like this. And now the problem is why this particular problem and why GA is to be applied for this problem is that the number of channels are very limited. Number of users are much more. So how to accommodate the users? Number one. Number two, that for the mobile users roams from one cell to another cell. Right? So while making the roaming, the call should not be dropped. No? Let's say you are driving and making a phone call. You want that when you move or when you switch over from one cell to another cell, the call should continue. So obviously, being in one cell, you have some set of channel or a set of channel allocated to one particular cell. Now you move to another cell, probably the channel will change. How to successfully take over? We call it normally in terms of the channel, we call it handover.
Soft handover.
Handover.
Hard handover. Soft
Hard and soft, both are there. Right? So the problem is of handover, let's say.
Yes, sir.
How to perform the smooth handover so that the call is not dropped. So this is the call dropping. Another is call blocking, that when you try to make a call, sometimes you find out that the channel is busy. It has reduced now, but initially it used to be too much because the channels were very rare, scarce channel. Number of channels are less. Many people are making call. So then obviously you get the channel is busy or something like this. During peak hours also when you talk and you try to establish the connection, you get these messages. So the objective is that these messages are not good for the ear. Isn't it? You are interested that we are taking the services. So whenever I try to, let's say, establish a call, I should be able to. Isn't it? That is what the objective is. Right? So the objective that we have chosen more or less in the whole sort of a channel allocation problem is that the blocking and the dropping should be minimized. Right? The blocking and dropping should be minimized. You can say this is the fitness function. Now how the blocking can be represented in terms of the channels, in terms of the cells that are there. Some cells are heavily loaded, some cells are scarcely loaded. So all these factors are to be taken into account. So there are a good number of constraints as well. Right? A good number of constraints are there for this particular problem. Right? So you see that the whole channel allocation problem is this. In fact, I have discussed some of the channel allocation techniques which are available in the literature, like fixed channel allocation, where the number of channels are fixed to the cells. Then there are dynamic channel allocation, depending upon the requirement, the channels are to be given. There is a allocation which is known as the hybrid channel allocation. Another technique is the borrowing channel allocation. We can borrow also, as we are dealing with the same within this cloud also. Sometimes you require, you can borrow also. So you are heavily loaded and you are getting a call. The channel is, let's say, the cell is receiving a call. Then probably we can borrow the channel, because right now we don't have, so we can borrow from our neighbor if the neighbor is having the free channel. Of course, this can be done only if they have the free channel. Isn't it? So that particular one is known as the borrowing channel allocation. So good number of techniques are already available in the literature, right? Borrowing channel allocation, etc. Now we do have applied the genetic algorithm for the channel allocation problem. You see that how we do have converted the whole problem into the let's say population, etc., chromosomes sort of thing. How we did this, and then where we tweaked with the genetic algorithm. So we converted the genetic algorithm just incorporating some sort of heuristics. So applying some heuristic in this meta heuristic, right? And the heuristic is like this, that we do have applied, is that in fact it has been observed from the idea has been borrowed from the plucking of the tea leaves from the tea garden, right? The plucking of the tea leaves in the tea garden. In fact, it happens to be that one of my students' brother was posted in Assam tea refinery, and what he said, that he observed that while plucking the tea leaves from the trees, in fact, he observed that these pluckers, they don't pluck each and every tea leaf. Rather, they just first test whether this is worth plucking or not, right? So they divided it into three, let's say. One which is not ripe enough, The tea leaf is not ripe enough to be plucked. They said leave it. Maybe we can do it tomorrow. We can pluck it tomorrow. By tomorrow it will be ripe enough. Right? Another is one which is rotten. Sometimes you forget to pluck, so that tea leaf is not worth hereafter. So that category is rotten tea. Right? The third category is one which is ripe enough and which is to be plucked. Right? Which is to be plucked. So again you can say how to identify, as in the morning he was discussing. Na? You can decide on the thresholds. You can decide on the two thresholds. Above the threshold, you can leave because it will be ripe tomorrow or maybe the day after tomorrow. Below the threshold, you can leave because it is a rotten tea. Now in between the two threshold, you can pluck those teas. This can be applied for the population, for the whole population of the genetic algorithm. Right? You know the population, a good number of chromosomes are there. Right? So we can see that which of the chromosome is good today. And which can be good. So for that we have chosen a sort of a threshold. So above this threshold, let's say we say that keep it for tomorrow. Below the threshold you just discard it, that hereafter you don't require. These set of chromosomes are not required hereafter, just throw it away. And the one which is lying in between can be taken for performing the crossover and mutation, for performing these operations. Right? So this is the idea which has been taken therefrom. Two thresholds have been generated. Two thresholds. How to decide on the threshold? Again, the problem here. And this is the same problem. How to decide on the threshold? For that we tested with some of the experiments. So empirically it has been decided. You can say. By testing, by let's say performing some sort of operations over there, and then testing that which of the chromosomes are, how to decide on the threshold. And once you decide the threshold, you can apply the same genetic algorithm thereafter. Right? So the same idea has been applied here, and we called it as the improved genetic algorithm. And I'll tell you just, and of course there are some other formalities that we have done, like how the chromosomes etc. have been decided. I'll come to that particular point. Considering all these, you just see that the paper was good enough to be published in IEEE transaction. So that is what I thought, that you have to have some idea that can click and that can be applied successfully. Once you do this, probably you have the good potential of publishing the paper anywhere in good journals, right? So you see that this was the idea, which in fact we applied not only on channel, many other problems also we applied the same idea, and it worked very successfully. Right? Many of them we applied it on mathematical. The first paper which was published applying this particular idea is in the Journal of Artificial Intelligence. Right? Thereafter we applied this idea in different domains. There we applied the idea on the mathematical function, only on mathematical function, just to test that how this idea works. And the paper was published. Thereafter we applied it on this grid scheduling problem. We have applied it on mobile computing problem, and so on. No. And we got some good publications out of that. Right? So the idea was this. ये क्या है? इसके बाद अगली स्लाइड है इसमें. इसके आगे की स्लाइड क्यों नहीं आ रहा? हाँ इसमें आ जाओ, इसमें आ जाओ और आगे नहीं इसमें नहीं और नीचे अब कहीं पे क्लिक करो. हाँ यहाँ पे ये वाले पे करो. ये देखो है ना, इसके ऊपर वाला यहाँ पे रहने दो, लेकिन इसके आगे चल नहीं रहा था, इसी के आगे तो रुका. नेक्स्ट वन, इसके आगे देखो रुक जाएगा ऐसे करने में. जबकि है तो वहाँ पे ले जाओ ना, सीधे मैं बता रहा हूँ. गो टू दिस पर्टिकुलर स्लाइड एंड देन इस स्क्रीन को बड़ा कर दो. I hope it is visible, right? I think full screen it is not working. नहीं इसके पहले तो यार वो था ना हमारा, ये भी तो है. ये 33 स्लाइड नंबर 33 उस पे रहो. ठीक है, इसके आगे करेंगे. So this is deciding on some sort of a chromosome that we have for this particular problem. What we did, what we did, we created a, rather than having the one-dimensional chromosome, we created a two-dimensional chromosome for this particular problem. And why the two-dimensional chromosome? Because in fact the channel allocation problem is this, like this, that the whole sort of a network, the whole mobile network has been divided into number of cells, right? The number of cells, and usually these cells are hexagonal cells for practical purposes, right? For practical purposes, these cells are hexagonal cells, right? So now once you design these kind of cells with a big network, you will find that each cell is surrounded by 6 neighbor cells, right? Each cell will be surrounded by the 6 neighbor cells. So now including the central cell and the 6 neighbor cell, total number of cells that we can consider in one chromosome is 7, right? One central cell and 6 neighbor cells, right? So we thought of having a chromosome of the two-dimensional chromosome of 7 cross 14. Now what is 14? 14 is this. The 14 which we said is this. And what it represents? It represents, you see, that 14, the length of this particular one cell information is 14, of the size 14, in which the first entry represents the blocked cells, blocked hosts, right? The second entry represents the free channels that this particular cell is having. Now the second entry represents the free channel that this current particular cell is having, right? Then the next 6 cells, actually they represents the lending information. 6 neighbors are there, na? So to which cell, neighbor cell, this particular cell has lended some of the channels, right? And the next 6 represents from which of the neighbor cells the borrowing has been done. Borrowing of the channels have been done, right? I hope you are getting it. So now this is the information of the one cell, right? This is the information of the one cell, and this way we can have a cluster of 7 cells with the central cell, 6 neighbor cells. You have the cluster of 7 cells, right? So now the one chromosome in this particular problem is consist of 7 cross 14, right? One chromosome is consist of 7 cross. Are you getting this? Right? So what we did here, again I will try to explain, that let's say the first one is representing the blocked host. A particular cell may have some host which is blocked, right? May have some host which is blocked, which it is not able to serve due to some problem. The problem is channel is not available, or maybe available given to some other cell, probably it has to take it back also, right? So the first one will let's say represents the blocked host. Next represents the free channels, how many free channels it has. Obviously you will find later that we have modified that if the free channels are there, then the blocking should not be there, right? If the free channel is available in the cell, the blocking should not be there. That we have removed, right? But the information is represented in the chromosome in this manner, right? Then next 6 information is about the lending to the neighbor cells. This particular cell has lended some of the channels, has given some of the channels to the neighbor cells. So which neighbor cell? There are total 6. So which neighbor cell, how many channels? That particular information will be carried out here in this particular one. And then remaining 6 will have similarly the borrowing information, right? The borrowing from which of the 6 neighbor cells this particular cell has borrowed some of the channels, right? So this is the way the chromosome has been decided. So now let's say one chromosome is 7 cross 14. This way you can have number of chromosomes to constitute one population of the problem, to constitute one population, right? To constitute one population. And then of course the pluck operation has been applied even in the initial population generation also, like borrowing decision. While making the borrowing decision also, this kind of idea has been applied, that while making borrowing, whether to borrow or not to borrow, right? The borrowing has not been done straightforward. Whether the borrowing may not, the borrowing should not lead to chaos eventually. So that kind of a decision has also been applied here. the crossover has been performed, and probably I have one example of performing the crossover. This is a reduced example because the 7 cross 14 becomes too large, so we reduced it to 3 cross 7. Just you can consider, because we do have to just consider that how the crossover has been applied. So you see that the two matrices are there. In fact, this is one chromosome, this is another chromosome. Decide on a cut point, that is the crossover point, and swap the values from the two. Swap the values from the two. Right? Swap the values from the two, you get two new offsprings. Like if you will find that 1, 2, 3 is there, 2, 3, 4 and 5, 6, 7. So these, let's say 1, 2, 3, 2, 3, 4, 5, 6, 7 is here. So this has been taken here and the remaining has been taken here from. But the remaining has not been kept as it is. As it is, it has not been kept. Why? Because we do have maintained the order there. And this has been done purposefully. Purposefully because it is a channel allocation problem. And in fact, while applying to this particular, let's say this kind of a technique, when you are applying on a particular domain, you will get the idea why this is not to be done. Right? So purposefully we did not do, of course it is 5, 6, 4, 7 and here also you have 4, 5, 6, 7. But it is not in the same order that you have it here. It is rather in the order this. So the order, like here you have 8, 7, 9, 4. Here also you have 8, 7, 9, 4. But the order, here 4 comes before 8. So that is why 4 comes before 8. So the order, of course, the digits are same, but the order is different. And order has been preserved from one of the parent. Here also the same thing has been done with respect to this. It has been done here. And this is problem specific. Right? These are some of the tweaking that we do have to do, which is problem specific. Like for for channel allocation problem, it is to be done like this, right? And then of course thereafter mutation, of course we did not apply the mutation, to be very frank, because while applying the mutation we observed that the mutation leads to convergence very quickly. This has been observed, which should not happen. But then we have gone through this and we found that applying the mutation has the weakness in taking this borrowing and lending decision. Borrowing the channels and lending the channels to them. And then we found that the mutation is not good to apply. And in fact, Professor Albert Zumaya also has worked a lot in the channel allocation while applying the genetic algorithm. And in fact, then we looked over the Professor Jumaya's paper and we found that he also said the same thing or observed the same thing that we have observed. Right? And that is why we have done away with the mutation. As far as the fitness is concerned, we decided the fitness based on this, which is more or less the blocking and dropping. Right? We said that the current block, next free, hot cell. Hot cell is one which is often heavily loaded cell. It has been called as the hot cell. Some of the cells are often heavily loaded. Right? So this is the one which we considered. Of course, some of the constant values we do have applied to suit the environment, because sometimes you have to give some constant values, right, with respect to that. And of course, thereafter some repair also has been done, because repair is required. Sometimes it may happen that after applying the crossover, you find that some free channels are being shown in the chromosome, but factually you have some blocked host. So then there is no meaning. You already have free channels. Why to keep the host as blocking host? So that also has been done away with by applying the repair. Okay? Of course, I am not going in detail, and in fact, again, the paper is available, which has already been published. You can go through that. Every detail has been mentioned there. Right? Why have been done this way? And then some of the experiments I can show you before ending this particular discussion. Some of the experiments that we performed is like this. The total number of cells that we have considered are 19 cells, because we do have to decide on some of the cells. So 19 cells. Channel per cell that we consider is 10. Crossover probability is 100% because mutation is not there. Right? Mutation has not been applied. Number of hosts in the network 50, 75, 100 and so on. In fact, a huge number of experiments have been performed thereafter. In paper, many of these experiments finds the place, but not in this particular talk. And then we do have considered with the different number of hosts, different number of channels, we do have considered that what is the performance over the time, and some of these algorithms like the fixed channel allocation has been considered with IGA, and you will find that the fixed channel allocation is always having more blockings, right? All these upper lines of the graph, and these are the IGA's performance, right? These are the lower one are the IGA's performance. In fact, here the representation is the blocked hosts, the average blocked hosts that are there in the cells. Thereafter, we do have compared it with the modified mutation GA. There is an algorithm which also has been published in IEEE mobile computing, transaction on mobile computing, and that was the modified mutation GA. So the algorithm has been compared with the mobile mutation GA, and in this fact, this particular one is the Albert Jumaya's paper, right? So it has been compared with modified mutation GA as well, and we found that over the period of time, of course, the modified mutation comes a little closer, but a huge number of experiments have derived that this particular technique performs much better than this modified mutation GA, right? So this is the one, and in fact there are so many other applications where it can be applied, this modified GA or the improved GA, and we do have applied for the grid scheduling problem eventually. Many of the problems it has been applied thereafter. I think that's all from my side. A conclusion comes like this, and then thank you. Now if you have any questions, then probably I'm open to that.
She has one question. She has a couple of questions, right? Go ask, don't worry. Ask, please.
You note it down.
She has noted down, so then she can.
Yeah.
So see that what I have tried to tell you is that what genetic algorithm is, how it works, where it can be applied, and then another possibility is that even you can think of just say altering a bit in the GA, in PSO, in any such meta-heuristic techniques, in any soft computing techniques. You can just, let's say, change a bit and you can get some sort of a good result. That is one thing. And another thing is that, as Professor Jemal was discussing yesterday, you can think of developing a new meta-heuristic techniques from scratch. Like what Tiger yesterday he was discussing about the tiger. But in fact you can, and we have many idea as far as the evolutionary techniques are concerned. There are many species in the nature that really optimize their prey. How they do optimize, that we can just mimic in the form of, we can have some mathematical representation of that, some sort of operation that we can think of that they do apply. Like many of the chameleons, you find they change their color just to catch hold of the prey. They change the color. So changing the color is one method that you can think of, and by the angle that they jump to their prey, once they reach near to the prey, how they jump, on what angle, the work is going on this particular direction also. So developing altogether a technique from scratch, right? Like I'll give you one example, probably you can think of, as far as the security is concerned. You know that the birds used to have their nest, and their nest is like this. One day I was just going through this, and I found that they used to build their nest in such a way so that due to heavy rain also the water doesn't enter inside the nest. So just can think of that what kind of let's say nature has given to the birds, that how do they frame. So you can just think of to design some sort of a system so that you can secure this particular system, right? So just have the idea, this particular idea, that how the water doesn't, of course there are many techniques by which the nests are built. Some nests are inside the earth also, right? So it depends on the bird, but on the trees that they put the nest, it is like this, that even the water, due to heavy rain also, water won't enter inside the nest. This is the beauty of the nature. And this particular one,
Tree selection is also.
pardon?
Tree selection.
Tree selection is also there. So you see that, and the cuckoo search is in fact based on this only. The cuckoos, they don't make their nest. Rather, they lay their eggs in the nest of the crows. And the cuckoo search, the whole cuckoo search has been derived out of this. So you can think of and you can have a new algorithm altogether, the new meta-heuristic technique from scratch. So the idea was this. Now, questions?
If I'm taking a multi-objective or many-objective problem, where do we use that GA? In its selection part, or if going to that what is it, optimization? Where do we go into
Both. For selection also, for optimization also. Because now you don't have one optimal function. Rather you have more than one, maybe two, maybe three. Right? More you add the optimal these objective functions, the more complexity will be added there. Then in fact, rather than generating one straightforward solution, you generate the Pareto solutions. Right? You generate the Pareto solutions thereafter. And then you choose what you have to compromise out of these solutions. Right? So the whole Pareto front is generated. And out of these Pareto front, and in fact the GA has been converted in terms of the Vega, NSGA, non-dominated, NSGA, NSGA2 of course, yes, NSGA. Yeah, many sorts of variants of the genetic algorithm to suit the multi-objective optimization problem. And in fact PSO also for multi-objective has been developed and is being used.
Actually, we have many we have many meta-heuristic algorithms. So then how we can identify, and we are applying at the scheduling program. So how we can identify that this particular algorithm, such as GA, is better for this parameter and PSO is better for this.
That is what I asked yesterday to Professor Jemal. Probably you are not here. I said that how they can decide on that this particular meta-heuristic will be suited for our problem, this will be suited, and in fact there is no straightforward method that this is the best for you. You have to, because it depends on many factors. It depends on the problem domain, it depends on the objective function that you are, it depends on the constraints. So you don't have a straightforward answer to this, that this will be suited for you, this will be suited for this, this will be suited for this. Nothing like that. You do have to apply, you do have to experiment, and do have to find empirically that what will be good for us. Like yesterday he has shown so many meta-heuristic, combined meta-heuristic, hybrid meta-heuristic also. Right? And then able to find it out that okay, this is suiting here, this is suiting. So you have to compromise somewhere here and there also. Sometimes the hybrid was not better in terms of the objective function, but in terms of the convergence it was better. You have to think that what do you want out of that. So it happens like this. No, nothing. Okay then, thank you very much. From my side it's over. इसका कहाँ है?